So, good morning everybody and welcome here to the Quantum Gravity 2023 conference in Nijmegen. It's really great to see so many faces in person sitting here and also in the virtual audience. So it's my great pleasure to introduce Sijbrand de Jong. So he is an experimental particle physics by training, but he has a big heart from theory, and today he will be here as in his function of a dean of the Faculty of Science to actually open this meeting. So please, the floor is yours.
Okay, Frank, thank you very much. I have to stand here somewhere behind you. Yes, good morning everybody on this Monday morning. Beautiful weather in the Netherlands. Welcome to the Faculty of Science. This in fact is not a building of the Faculty of Science. For some of you who know it, the Faculty of Science is on the other side of the road. Not to miss mint green buildings. My name is Sijbrand de Jong. I'm Dean of the Faculty of Science. This is a temporary role. Frank already said my background is experimental particle physics, but I'm interested in theory. And I was just thinking that, in fact, I'm one of these people that live on your background. Although I never did anything with a curved background. For me, everything is flat as a pancake. Yeah, so welcome on behalf of the Faculty of Science. I'm actually thrilled to see so many people in this lecture hall. I understood that there are also a good number of people online. Sorry for the folks online, you don't know what you're missing. Nijmegen is a really nice town, and our university is a really nice university with a nice campus, and especially with the weather like today, and I hope this week it will not rain too much. It is very pleasant to go outside and have a stroll through the park. Because this is, of course, one of the aims of the meeting. One always thinks that the aim of the meeting is to sit in a lecture hall and listen to talks. No, the aim of the meeting are the coffee breaks and the lunch breaks and the evenings. And we use the lectures as an excuse. So please mingle and talk to each other. This is where great ideas come from. They seldomly come from a talk, I must admit. Well, not the original idea. Of course, working out the idea is also important. I understood that this is part of trying to build a community for quantum gravity, and I think this is a very good job. And I also would like to thank the organizers, Frank, of course, Timothy, I saw Beatrice, some of the others, for organizing this. I think it is a very good idea to form a quantum gravity community, because I could hardly think of any more important issue to solve, but then I'm biased. Of course, we have other nuts to crack, like climate change, etc. But I think quantum gravity is one of these fundamental things that we really want to understand. Okay, this is like a stone in your shoe that we cannot understand. This marriage between quantum physics and gravity. So I wish you all the success in doing so, and in having very nice conversations among you, and in, of course, interesting lectures as well, as a bonus for this meeting. So please be welcome again, and have a very nice meeting.
Slide, the ISQG. So then it's also my pleasure to welcome the representatives of the International Society of Quantum Gravity, who is actually patronizing this meeting. And I give the floor to Daniele Oriti.
Yeah, hello. So thanks again for being here. So I only have two things to say, so I'll be brief, Bianca, don't worry. So the first one is that we established the International Society for Quantum Gravity a little bit less than 2 years ago, with some clear goals in mind. One is to support, promote quantum gravity research in all its aspects. conceptual, mathematical, phenomenological, and so on. And then to support young researchers in the community as much as we can, and then to bring different sub-communities together. So focusing on shared issues, try to establish links and contrast, compare perspectives to establish a solid dialogue across sub-communities. And I'm happy to see from the program that the organizers of this conference clearly share these goals, and they've really taken on board our objectives and the spirit of the society. So the first thing I want to say is thank you to the organizers for this, for really sharing the goals and taking on board our objectives. The second thing I want to say is to encourage all of you who are not already members of the society to join. It's for free, so I don't earn anything by saying that. Because we need the contribution from as many members of the community as possible within the society to have more activities and to be really representative of all the rich set of ideas and perspectives of the members of the community. And the more we are, the more representative we are, the more weight we have towards the outside world. And this is going to be even more important in the next few months because we are in the process of establishing the society fully, including the legal aspects. And so there will be a constitution to approve, there will be roles within the society to elect. So it's really important that as many of you as possible join and contribute to this process. So that was the second thing. And the third one, in fact, I lied. There were 3, not 2. Enjoy the conference.
Okay, our dean is gone, so I can contradict him now, saying that also science talks are important for this conference. So I think it's a crucial element that we learn what each other in different communities are doing. And I'm very happy to introduce the first speaker of the morning session, Bianca Dietrich. So she has been faculty at Perimeter for 10 years now, a little bit more. And her background is in loop quantum gravity, spin forms, and recently also in Lorentzian computations. And she has also been the key organizer of the predecessor of this conference. So if you were around for Quantum Gravity 2020, this is the person who made it happen. So when we looked for a speaker that can actually summarize the key challenges of the field, I was very happy that she immediately said, yes, I can do this. So and now I'm very curious of what you will be able to tell us. The floor is yours.
Thank you, Frank. Let me first thank the organizers of this nice conference. That's Frank, who did a lot of work. I understand Renate, Beatrice, Antonio, Timothy, and Badri. And I know how much work it is, and it's even in person. So it's great to meet here. So the organizers asked me to talk about common challenges. And well, I will talk about some of these challenges. As it is in quantum gravity, sometimes we don't know what we don't know, so that's part of the issues. But let us try to cover what we might not know. So quantum gravity is a very vast field, and since I will come to that, we have not so many experimental clues yet. And there's really a nice diversity of ideas, and well, I've taken this picture from the ISQG webpage. I might try to identify your approach in this picture. So since we have this diversity of ideas which start from different starting points, it's really important to learn from each other and to look for shared challenges and principles. And so, of course, I will present only a biased selection of these challenges, and you might find more in this NOMAS paper we wrote last year. And the first challenge is that our universe is Lorentzian, at least most of the times. But why is that a challenge? So it's a challenge because, well, a big part of the work which has been done in quantum gravity has been actually done in Euclidean approaches. And possibly the younger people here might ask, why the hell did you do Euclidean quantum gravity if we know that the world is Lorentzian? And so let me first define what do I mean with Euclidean quantum gravity. Kind of the standard definition is that you, for instance, take the path integral, you do sum over Euclidean geometries, so geometries with Euclidean signature, but you also sum that not with a really quantum mechanical weight, but with a statistical weight, with the exponential minus the Euclidean action. And you have to compare that with, say, the Lorentzian path integral, where you do sum over Lorentzian geometries with a weight which is really the quantum mechanical weight. And why have Euclidean approaches played such an important role? Well, first there was just a practical issue of being able to do computations, and so Monte Carlo simulations, in particular if it came to non-perturbative approaches, were really the standard tool to address quantum field theories like QCD, were highly successful, and so the same philosophy was applied to quantum gravity. Also, this Wick rotation, which basically rotates you in principle from Lorentzian to Euclidean theories, has been a hugely successful tool in quantum field theory. In addition, you have thermodynamic interpretations. But of course, this Euclidean approach in case of quantum gravity comes with quite a number of drawbacks which do not necessarily appear in quantum field theory. So one important property of Euclidean action in quantum field theory is that they are bounded from below. And this is not the case anymore at all for Euclidean quantum gravity, where the action is not bounded from below. And again, in particular for non-perturbative lattice simulations, what happens is that it tends to drive the system into regions where the action becomes maximally negative. That's when the so-called conformal factor is maximized. And so for instance, in Ricci gravity, where you look at different lengths are the variables, you get so-called dominated by spike configurations, where you get very spiky contributions. In dynamical triangulations, which kind of glue triangles together in all kinds of ways, you get so-called branch polymers, which you see an example here, which basically dominates, again, this phase of weak gravity. And so similarly, in other lattice approaches with other variables, you basically fail by being driven into this phase where the conformal factor is maximized. Another disadvantage, or an advantage, as a disadvantage for Euclidean quantum gravity is that the configuration space of Lorentzian geometries and Euclidean geometries, well, it's very different. So whereas in quantum field theory, you try to define the Wick rotation as a one-to-one map, it's not possible at all in quantum gravity. And well, the people which advertised that most were basically Renate and Jan, starting causal dynamical triangulations. And so they combined these two disadvantages to an advantage in basically restricting to Lorentzian configurations and managing to get rid of these annoying configurations like the branch polymers and see nice phase diagrams where you do get interesting four-dimensional geometries. Another feature which you don't necessarily see for Euclidean triangulations is that you cannot rely on destructive interference, which might cancel out unwanted configurations. And one such example might be explained by Sumati and Steve in the case of causal sets. So one big reasons why Euclidean approaches have been done are computational techniques, where Monte Carlo simulations really is a working horse for in quantum field theory to do non-perturbative lattice calculations. But luckily, in the last years, there were more and more approaches to do really Lorentzian path integrals. It's not only important in quantum gravity, but it's a general subject of doing so-called real-time path integrals in quantum mechanics and in quantum field theory for various reasons. And so possibly the best known technique you can do is to deform your integration contour, and that works on a semi-classical level and on a numerical level. So numerically, you want to deform from a highly oscillating integral to a contour where the integrand is decaying. And the best choice you can do are so-called Lefschetz symbols, where you replace the oscillating phase with really the decaying, maximally decaying phase. So this is good for numerical, for semi-classical approximations and explicit numerical integrations. Now, there's also a technique which combines these Lefschetz symbols with Monte Carlo simulations. Here the idea is that you first use the so-called gradient flow to flow the system to the Lefschetz symbols. So the gradient flow is there to identify the Lefschetz symbols. This gives you a non-oscillating phase, and then you do Monte Carlo simulations. So this is a very nice idea. My impression is that this is so far at a more experimental stage, because there are some free parameters you have to choose for the flow. And in some cases it does work, in some cases it does not work very well. So we have to learn more in how reliable it is. It's not as much understood as Monte Carlo simulations just for Euclidean systems. A quite new technique which relies on actually very old ideas are so-called acceleration operators for series convergence. And here you can treat sums and integrals, and I will talk about it in the next slide. Other techniques are tensor network renormalizations, where you rely on an explicit summation with some truncations. So here you can also use real space integrals. Basically, for more complicated systems, simulations have been done up to three-dimensional systems, including gauge theories. And I know, like the Ising model has been done in 4 dimensions, but it's a real challenge then to scale these things up to kind of complicated systems, such as quantum gravity in 4 dimensions. Also in asymptotic safety, in the last years, there have been much more work on Lorentzian signature asymptotic safety. The issue here is not so much to solve the path integral, because instead you look at flow equations, but still there's a number of questions you have to address on the Lorentzian side. That includes a nice parameterization of Lorentzian fluctuations. And of course there's quantum simulations now, machine learning, but here the questions. So this is just in baby shoes, so to say. The question is, can we scale up these techniques possibly to ever treat quantum gravity? So this is more to be explored. So here is the first challenge that indeed, luckily, we have a number of methods now, but we really need to find better methods and to be able to scale them up to larger systems. And let me present this acceleration technique for series convergence and just 2 examples. So these are real life examples from quantum gravity. It's where we wanted really to treat a sum which is with an oscillating phase. And here you see the results of the partial summations, of the partial sums, up to 100,000 terms of a mini superspace example. And where you see a block, the reason is here that these are lots of points, and these are highly oscillating, so you see them piled up in this block. And the oscillations after 100,000 terms are still much larger than the final result. So if you have to, even if you sum to 1 million, which I did, you still find oscillations which are larger than the end result in absolute terms. So you would have really to sum a very long time, like, I don't know, 10 millions to have a decent convergence. And you don't want to do that because in the end you want to treat many of these sums. But there's an old technique which comes really from the 40s and 50s, which I guess many have forgotten now. It's actually implemented in Mathematica. And here you see a comparison. So it's really a series transformation. You take this series of, which is very oscillating, you apply a nonlinear transformation. The ideas are quite simple. You can check it on Wikipedia on a Schenck's transform. And computing this transformation takes like less than a second. But here you see the result of applying this transformation to the first 100 terms of the series. And you see immediately, well, not immediately, but after 50 terms, a nice convergence. And at 100 terms, the relative error, that is, if you look at the last 5 or 10 examples, it's less than 10 to the minus 11. So it's a really nicely working technique in this case. And you can also treat cases where you, for instance, compute the expectation value. Then you get something which clearly does not converge, it diverges. But if you kind of take out the oscillations, you again find a nice convergence with a very small value here. Because it's so small, the relative error is a bit larger. And so these are really nice techniques. They're not guaranteed to work for everything, but they seem to work very well for actually these kind of sums where we have an oscillating phase. One condition is that the action for these systems, if you consider a discretized system, should be at most linear in the summation variable. But this is typically the case because the action is an action, and typically discretization appears in terms of h bar. So this will be the case, and in fact it's the case for spin forms in 4 dimensions. And so you might wonder, why is it important that it's linear in the discretization variable? Here I show you just a very simple example of a quadratic action. And here it's just the partial sums. You can try it yourself with Mathematica, and you see a very mysterious staircase behavior for these partial sums. So you will wonder, well, to what thing does it converge? And the reason why you get these staircase behavior is because about an interference effect between the discretization and the oscillations. So here what happens, because it's quadratic in this discrete variable, the frequency of your oscillations are growing linearly. So the frequency constantly increases, and you get so-called pseudo-subtle points. That's when you have a discretization which basically probes only, say, at the top of your oscillations. You find these so-called pseudo-subtle points which you see in the discrete, but not in the continuum. And this will always appear if your frequency is always linearly increasing. And so this explains this funny staircase feature. And so for these kind of oscillating sums, well, it's very hard to find any convergence. But again, that might not appear actually in quantum mechanical systems. So we have these more techniques. Another question you might ask in Euclidean approaches, it's basically the conformal factor problem, which basically killed most of the Euclidean approaches. Does it still appear in Lorentzian quantum gravity? And so if you look at the deformation technique, there's a convergence criterion to select your contour, automatically selects the right contour. Whereas in the Euclidean approach, one way to treat the conformal factor is to rotate it by hand to the other sign if you can actually identify the conformal factor. Which you can do in continuum approaches perturbatively, but often not in numerical approaches. And so let's look at one example. If you do a one-loop evaluation of 3D Redshift quantum gravity, this you can do by just chopping up the problem in so-called Pachner moves, where you integrate out just one variable, as we will see. And there are two such moves. One where we have to integrate out one edge, which goes through two tetrahedra. Actually, 3 tetrahedra first, and you are left with 2 tetrahedra. In the Euclidean case, you get something which is just Gaussian. In the Lorentzian case, you get something which is a Gaussian with an I, or a Fresnel integral. So these p's are positive numbers. And so you can just do these integrals in both cases. The other kind of move is for one move, you have to integrate 4 variables, 4 edges here. But you will find that 3 of these are gauge modes, so we are left with one mode. And this happens to be the conformal mode. So in the Euclidean approach, you get an inverted Gaussian. And so here it's where you would have to define by hand. I change the sign by hand. That's not necessary in the Lorentzian approach, where you get again something with an I. It also has the opposite sign from the 3-2 move. But this integral is still well defined. So you don't need to do anything to treat the conformal factor in the Lorentzian case. Similarly, one big issue in redshift gravity are spike configurations. And there's been an old discussion by Jan Ambjorn in France that the expectation values of length operators turns out to be infinite in Euclidean quantum gravity. So actually, if you look at higher dimension redshift gravity, look at the minus Euclidean action in these spike configurations, where you get just something with an exponential increasing amplitude, which will always give you infinity if you try to integrate over it. But it's finite in Lorentzian quantum gravity. And in fact, I showed you the example a few slides ago, which actually computed these expectation values and gave you something finite. So, well, there have been lots of Euclidean work on Euclidean non-perturbative quantum gravity approaches, and the big question is, how much can we rely on the results of these approaches to see whether what they do say about the Lorentzian versions of these approaches. Another aspect, which I mentioned before, is this Lorentzian versus Euclidean configuration space. And again, these are insights which started with causal dynamical triangulations. So if you have a Lorentzian geometries, well, you have a light cone structure, and as we know, typically each point has exactly 2 light cones, a future one and a past one. And a mathematician would call that a Lorentzian geometry, but usually would not call this a Lorentzian geometry. And here what happens is that you have some points where you, for instance, have 4 light cones. That happens if you have so-called trouser configurations in 2D, or even 0 light cones. And so here I have a irregular light cone structure. So I will still call that a Lorentzian spacetime. And here you see a Euclidean spacetime, where you get a bit of idea that there's much more space for getting arbitrary Euclidean spacetimes, where you wouldn't care about these so-called baby universes with these fingers, or even other topologies and holes in your manifold and so on. And so that indeed is the mechanism behind causal dynamical triangulations, which does not allow such configurations. And was a big physical insight of Jan and Renate, but only allows not really these boring, that looks boring, but it could be that, there's a very interesting Lorentzian geometry which everywhere has 2 light cones. And so it leads to a new universality class of random triangulations with an interesting continuum limit in 4 dimensions. So, this approach is called causal dynamical triangulations because these conditions are interpreted as causality requirements. However, if you do causal sets, then these kind of configurations are actually allowed. So that's why I call them light cone irregularities. So here, causal dynamical triangulations and causal sets have quite different philosophies concerning these configurations. Of course, in causal sets, causal structure is basically the most important ingredient here. But I will ask this question for causal sets people. Well, should you get imaginary terms in the action? And the reason I'm asking that is because in Redshift gravity, one does get imaginary terms in the action. And so you can ask what happens for other approaches. So far we have been in the realm of quite combinatorial approaches. In Redshift gravity, you typically fix the triangulation, but look at varying edge lengths or other geometric quantities. And what happens is that, in fact, you see these kind of configurations where you have an irregular light cone structure quite generically. So it hasn't been investigated yet how generic it is, but if you make simple exercises, you see that they appear quite generically. Here I just drawn the simplest example of taking 4 triangles. It's a Lorentzian triangulation with only space-like edges. And you can easily tune the edge length such that you get 4 light cones, or also 0 light cones at this center point. And how you should interpret that is that you have this configuration at the trouser, or the so-called Yarmulke. And such configurations even appear in mini-superspace cosmology, where Seth Asante will talk more about that. The results of the path integral indicate that we should actually include these configurations in the path integral. And interestingly, these configurations come with an interesting complex structure. So we can consider the Redshift action now as a function of the length variables, and we complexify the length variables. If you do that, you see that the Redshift action comes with branch cuts for these kind of configurations. And along these branch cuts, well, you have imaginary contributions. Also, you can just consider a Lorentzian configuration. But these imaginary contributions come with opposite signs. So here's an example where you choose a time-like variable among your edge lengths, and you complexify that so that's a complex plane. What you will nicely find if you consider this concept of a complex Redshift action is that it reproduces the Lorentzian action along the real axis with both choices of overall sign, and the Euclidean action, again with both choices of overall sign. So that's very similar to the Wick rotation. But you have also a branch cut along a part of the real axis where you have these light cone irregularities. And because these come with opposite sign, you have basically a side where you enhance such kind of configurations and a side where you suppress these kind of configurations. So in fact, then you have to consider the question, which side of the branch cut should I choose? And if you choose a suppressing sign, well, that gives you a mechanism to suppress such configurations without forbidding them explicitly. So forbidding them explicitly would be quite involved because these are kind of non-local conditions. And it's a possibility to reconcile the findings of causal dynamical triangulations and the philosophy of causal set to include such configurations, but to have also a mechanism which suppresses these. Okay, we'll come back to this question of sign. So you might wonder, okay, this is redshift gravity, I'm doing continuum, why should I care about these weird things? And so the question, does it appear in the continuum? And is it relevant for something? And so the answer is, well, again, these complex structures have been indeed discussed in the continuum already a while ago, and possibly the first paper doing that is in the context of topology change by Jorma Luku and Raphael Sorkin. And recently this has been kind of an inspiration for an article by Witten, which indeed said, well, if you have to complexify, what kind of complex matrix should I really choose? And which should I include in the path integral? Also, there have been a few works where it has been noticed that actually the gravitational action is possibly indeed complex and has imaginary terms. And concerning the gravitational thermodynamics, there's basically a paper by Don Marolf, where really the title is Gravitational Thermodynamics from Lorentzian Path Integrals. And his aim is really to derive thermodynamic entropies from the Lorentzian path integrals. And he argues that in order to do that, you have to introduce codimension 2 singularities. And the interesting thing in redshift gravity, these appear naturally. You don't have to introduce them by hand. And the reason why you want to introduce these singularities is exactly to allow for these kind of light cone irregularities in your path integrals, and they also appear in recent discussions for replica copies and resolution of black hole information paradox. So it seems that these are really relevant configurations. And in fact, if you want to get to entropies, you might have to choose actually the opposite sign to get these entropic contributions for the branch cut. So, well, overall, these are quite new developments with a few exceptions. And so there's certainly space to understand better the role of complex matrix and complex actions for the Lorentzian gravitational path integral. You know, it's very interesting whether you can accommodate them in the canonical formalism. And in general, well, there's a question, should we include configurations describing topology change? And what happens, for instance, in the complex actions if you consider the sum over topologies? Again, sum over topologies for a long time was done in the Euclidean approach, where you don't even see these complex terms. Okay, so to summarize, well, we do have now more techniques for Lorentzian quantum gravity, and that's very nice because in the end we want to do Lorentzian quantum gravity. If you do Euclidean quantum gravity, you can't really answer questions about causality and all the interesting things, but we also need more techniques for doing Lorentzian quantum gravity, in particular for having many variables to deal with in the path integral. And the main reason is that the Lorentzian configurations come with additional structure of having causal and light cone structure. And these can be often irregular, and we have to decide what to do with these configurations. Interestingly, they come with branch cut for the action and imaginary terms. So here's an interesting open question, which side of the branch cut we should choose. And these configurations, but also the Lorentzian path integral, actually allow for thermodynamic interpretation. So I do think that there will be lots of developments in this direction. I will come to basically that will be the next topic. And that's a question of what is the structure of quantum space-time, apart from being Lorentzian. And that starts with a topic of observables. So Klaus will give a focus talk on this question, so I won't talk too much about these issues, but it's something you can start with and derive interesting consequences from quite simple considerations which start from observables. And the main issue here is, well, in quantum field theory, we work a lot with fields, as the name suggests. These fields are evaluated at space-time points, and the main objects are, you could argue, are endpoint functions, which indeed allow to reconstruct the full theory and the full dynamics of quantum field theory. But in quantum gravity, you want to implement diffeomorphism symmetry and invariance, and so these fields are not observables at all. So also you don't have any endpoint functions. So here's the main idea, which is really quite old and goes back to Einstein, is to use relational observables. So that's to ask what is, for instance, the field evaluated at a point where in 4 dimensions 4 other fields take certain values. And I guess we have quite a number of talks about relational observables. And so in principle, this idea is, you can implement it, it works in various approaches. You can do it covariant or canonical covariant in all versions. But actually the issue is that, well, if you take some phase-space functions here or some fields, these fields, well, they will, if you take realistic fields and relativistic fields, they will not really serve as perfect clocks. So it's really hard to construct something which always goes forward and is monotonistically increasing. So, if you do not take artificial matter, for instance, dust, it seems there's not really any perfect clocks in a closed universe. And there have been, by now, quite a number of literature exploring the consequences of this fact. I will explain one consequence regarding locality and the power of resolving basically measurements. There's questions about what happens if you have only chaotic behavior, and so in particular no monotonically increasing functions, which, the investigations which have been done by Martin Boyewald, Philipp Höhn, and others, and also questions about, well, what happens if your universe starts and ends? By definition, well, there's no field left which you can use as a clock, and so it comes also with the question of unitarity, and you can go to talks by Steffen Gielen and Menendez Pidal, I guess. Let me come basically to this question of how much can you resolve quantum measurements? To that end, you can look at commutators and how much measurements influence each other. And basically, even in classical field theory, using just this idea of relational clocks, you could investigate the commutator. So it's a straightforward computation if you apply enough approximation, and you find quite theory independently the usual result, that is the Green's function or the commutator function, which you usually get in your field theory evaluated at these points which you define by your clock fields, but you get an extra term, which looks a bit complicated, but essentially is 1 plus the energy of the field you want to observe, defined by the energy of your clock fields. And so if you want to make it small, it's very intuitive that you have to increase the energy of your clock fields, because you can only observe as sharply as fast your clock is. If you have a slow clock, well, that gives you very low resolution. So in principle, well, you want to increase your clock fields, and also you want to fill the portion of space with your clock fields which you want to observe. And so these two conditions give you a bound, and that has been well, investigated first by Steve Giddings, Don Maroff, and Jim Hartle, and the covariant approach, where basically they derive a locality bound, because the argument is if you increase this energy too much, what you eventually will form is a black hole, and that restricts your ability to have a high resolution. And so what I like with this argument is very basic calculations and very basic ingredients. And you can look even at much simpler systems, like the arrival of time operator. Again, the arrival of time operator is very similar to using a relativistic clock, because you use as clock basically your particle position, and that's quadratic in the momenta. And that happens with all kinds of relativistic clocks. And if you write down your arrival of time operator, technically there's this technical point which is that it's not, you cannot make itself a joint. And so you think it's a very technical point, but in fact there's huge literature on the time of arrival operator and its physical consequences. And so one paper is on deriving a new kind of uncertainty principle. Again, it's a bound on resolution, which basically says the resolution you can get with, or the uncertainty in your time measurement is bounded not by involving the uncertainty of another operator, but just involving the energy of your particle. And so there has been a very careful discussion by Haranov, Unruh, and a bunch of other people. And basically the same arguments holds if you use these relativistic clocks. If you don't like these kind of canonical or covariant commutator calculations, other people have just looked at scattering for ultra Planck scales. And here the argument is if you really go to very high energies, what will eventually happen again is you form black holes. And these black holes, well, they evaporate eventually via Hawking radiation and hide the process of ultraviolet high energy scattering. In fact, what you get is rather lots of soft gravitons doing your momenta exchange. So it's also kind of UV infrared mixing. And so you have a similar mechanism that the forming of black holes hides really ultra high energy scattering and the resolution of these processes. So there's a general challenge which is to better understand the type and algebra really of observables and the properties of observables, given that we have relativistic clocks and the possibility to find kind of new fundamental uncertainty principles. And so these are partially quite old considerations. Eventually they come really that we are very much used to quantum field theory where space-times mostly acts as an index set, but this index set becomes quantum. And we have to deal with it. And so we can ask what is then the resulting structure of quantum space-time. And so a number of approaches have kind of started with this question and made proposals to either replace basically classical spacetimes more or less directly with either fractal spacetimes or fractal dimensions. Non-commutative spacetime really starts from these heuristic arguments of not being able to resolve measurements in two independent directions. By loop quantum gravity and spin forms, there what you find is that you have geometric operators, which also in some sense give you finite resolution because they come with finite spectra and so on. Other approaches are a bit more radical and basically are based on the idea that eventually you have to reconstruct space-time from some underlying features. And depending on your viewpoint, there's basically this list of approaches, which includes holography, local holography, matrix and tensor models, group field theories, strings. You can have also area matrix, which are different from length matrix, twistor space, relative locality, and Born duality. These all start with the idea that what you should start with is not space-time, but possibly the observation of momenta and momenta exchange. And so what would be nice is actually a better connection between observable algebras and properties and their symmetries and the structure of quantum space-time, which you postulate in order to compare this on the level of observable algebras. Let me come to the next challenge, and that's reconstructing our universe. And so typically, you start with very, very radical ideas on a very fundamental level. So here I take something, for some reason it's called a set, and then I have to reproduce our universe with all the examples of galaxy formation, the Big Bang, our Earth somewhere. So and the challenge is, of course, that you have to bridge an enormous number of scales, which is unprecedented in physics. And you can understand the problem of quantum gravity as a problem of defining really consistent theory, which is valid on all scales. Here, this idea of bridging these scales, for instance, using the renormalization group, is one starting point to develop a common language for quantum gravity approaches and the emergence of space-time. And so if you would be really able to do that in a more straightforward way, that will also allow us to derive quantum gravity signatures. But there is this sentiment, basically, that so far we have not seen any signatures of quantum gravity. In fact, you might deduce that from a title by Giovanni Amelino Camelia, which is basically, are we now really at the dawn of quantum gravity phenomenology? So possibly we are. It's very hopeful that we find more and more measurements where this is the case with multi-messengers, astronomy, gravitational wave, and now nanograph and so on. But since we will have an entire session on this, all these new exciting measurements, I will not comment too much on that, but comment more on the many features that our universe has already, which we know about, which ask for an explanation. And so that depends on how radical you want to be in order to explain certain features. And that includes fake quantum theory. If you don't put it in your approach, you might want to get it out. The fact that, at least on macroscopic scale, you have a four-dimensional smooth space-time, Lorentzian signatures, also gravitational dynamics, small and positive cosmological constant. Do you need some extra field for inflation, or does your quantum gravity theory provide a mechanism for inflation or explaining standard cosmology? The fact that we seem to need initial conditions, but they're also quite simple. Can you explain matter from your theory? And the kind of matter. Can you explain dark matter? And the types of matter and values of the matter couplings. And of course, some of you might say, I've solved that already, that's great. And we can discuss. But in general, I guess there's not really one approach which has solved all these things. So happy reconstructing and deconstructing and the rest of the...
So thank you, Bianca, for this very nice talk and leaving time for questions. So is there anything the audience still wants to know? Yes, please. Just wait for the microphone to arrive and then everybody will be able to hear your question.
Well, perhaps a bit crazy question. So, from some statement of your talk, I had an impression that perhaps we can say that the black holes can be created as a consequence of observation procedure. Is it true that when we observe, we should apply additional energy? It implies an impossibility of large energy, and this creates black holes. So, can we see that the black holes is an observation artifact?
I think the argument relies on the fact that if you want to resolve space-time processes at very, very small distances, you need always high energy.
Yeah.
And so, in particular, if you want to resolve these very small processes also on a larger space-time region, where you need to concentrate high energies in a given area, and you can only do that up to a certain point, after which you do form a black hole. So that's just a theoretical fact, which relies on theorems that say you do form generically black holes if that happens. People have been speculating that might happen in the Large Hadron Collider. That has not happened yet. But there have been these calculations, for instance, at some point in case quantum gravity scales down. But this is a general idea. And so the arguments are very similar to old arguments which have been done about the Heisenberg uncertainty principles, which are basically also very similar, that if you want to observe something, you need a photon, and that needs a certain energy, and if that arrives at your particle, it will disturb the particle. So here it's really, however, new that this black hole formation comes really from the property of having a gravitational system.
Yes, there's a second question from the audience.
Yeah, I didn't want to ask a second question. I would just like to continue on this black hole thing. The argument that the black hole forms when you put large amount of matter into a small enough amount of volume rests on the assumption that general relativity is assumed to hold at those scales. But typically we do not know that, right? So we assume that there will be quantum corrections to GR, to Einstein's equations. So we really don't know if a black hole will form or not on those scales. So it might happen that we get quantum contributions or quantum corrections to Einstein's equations so that the black hole does not form at those scales, so that you can look at smaller distances without having this limit. So
yeah, I guess
it's a loophole to this argument, basically.
Yes, it depends also on how much a region you want to resolve, basically. Because I guess at some point you do say that, you assume that gravity holds for larger regions, and then you do expect that these black hole theorems still apply and form a horizon. So I guess you have to differentiate between having a horizon and possibly having really black hole similarities. So as soon as you still have a horizon, you might still see these effects. So it depends on whether your modification is strong enough to resolve horizon formation. Which, you know, I typically think that most theories still allow for horizons.
Okay, Alicia, then it's your question.
There's a question from Sue. So Deepan Betal, he's asking, when considering quantum matter fields in quantum gravity backgrounds, will there be any changes in the renormalization of the matter theory due to the UV and IR mixing?
Will there be any changes?
On the renormalization
Well, there will be changes,
of
yes,
the matter.
because already at a very basic level, you will always get, for instance, graviton loops, so that will still contribute, and Frank is an expert in that. And indeed, when I say coupling constants, that is from considering the interaction between matter and gravity, and it's Astrid Eichhorn which pushed it quite a lot to get predictions from quantum gravity for coupling constants of matter by considering the question or by postulating that quantum gravity should be still asymptotically safe. So do you get UV infrared mixing? Well, the system I was describing, or these examples, do involve matter. So this idea comes from scattering matter particles, and the question is indeed, if you go to high enough energies, do they form black holes? And the idea is that black holes, in the end, are more infrared phenomena. So in that case, you get UV infrared mixing.
There's one more question by Renate Loll.
Yes, hi. Well, thanks for a beautiful overview talk, and thanks for highlighting the larger perspectives, right, and the common issues. So for the Lorentzian story, which I think, of course, yeah, is close to my heart, so you presented a number of, new ideas. Now, as we've also learned, from something like looking at non-perturbative lattice approaches, well, there is, of course, at the end of the line, you want to do these things not just for perturbative systems and for, quantum cosmological systems, but for the whole non-perturbative story and the full quantum field theory. And then, of course, if you look at something like CDT, of course, we can introduce these more irregular configurations, but then the question is, can you in the end actually do the sum, and does the sum make any sense whatsoever? So which of these approaches is, you listed there, of the new ideas is the most promising in that regard, you would say?
You mean the calculational techniques?
Yeah, you had a whole number of bunch, new ideas, maybe not some not so new ideas.
Okay.
Going Lorentzian.
Yeah. So most of the, some of the calculational techniques have been only explored indeed for systems with few variables, and but the works are quite recent, so I hope one can push them to higher dimensions. And hopefully, possibly, it might be some combination of tensor network techniques or ideas which come from tensor networks, which is finding reasonable truncations. So in some sense, tensor networks sounds a bit scary, but the idea is really to find best truncations for your renormalization flow. So best truncations where you only throw away irrelevant terms. And for instance, these summation techniques. But mostly it is an open question, so where we have to develop techniques which can hold for systems with more variables. So one thing which is explored in QCD are these holomorphic gradient flow systems. But my understanding is that it's more subtle than standard Monte Carlo Euclidean simulations. And then you can always hope on quantum simulations, I guess, and machine learning, but unfortunately what I've seen so far are simulations which might see quantum gravity, but they involve like angular momentum systems of one or two few spins, so we have to be hopeful or indeed tackle, on the other hand, the other questions. How much can Monte Carlo simulations tell us about simulating the full Lorentzian path integrals?
I think there was one more question from here. If you can make it brief. No.
Yeah, thank you very much for the nice talk. So since we're talking about fundamental issues, one of the problems that usually is kind of put under the rug, as in on par with problem of time, is the problem of collapse of the wave function. And so I personally like the version with the decoherence. Well, the whole universe is already in the superposition, but locally it looks like it's not.
I hope Klaus would talk more about that.
So okay.
I didn't want to talk about decoherence with Klaus.
Okay, so okay.
Okay.
I'll wait for that.
Then let's move the question to the next talk. Store it safe. Brief. Okay. Someone signals me I should watch time. Yes. And move to the second speaker of the morning session. So, the second talk of this opening session will be by Klaus Kiefer. So, Klaus Kiefer has been professor for theoretical physics at the University of Cologne for at least 20 years. So, his research interests are mainly based in quantum geometrodynamics, so very conservative approaches to quantum gravity. But he is also very famous for all the reviews that he has written and also many, many public articles that appeared in German popular science journals like Spektrum der Wissenschaft. And then what I really hold in very high regard is his textbook on quantum gravity. So this is really an invaluable source and one of the rare books that really tries to go beyond a single approach of quantum gravity and give a a broader review on the field. So it's a pleasure to have you here giving the talk, and the floor is yours.
Yeah, thank you very much for this kind invitation, this kind introduction. It's of course a pleasure for me to be here. So in the following half hour, I try to give a focus on one issue in quantum gravity, the problem of time. Now because,
You're out of view of the camera.
Because of the camera. Oh, sorry, I did not know. Still very old-fashioned, I must say, walking around in the lecture hall. The issue of time. Now, this is, of course, a comprehensive topic. So in this half hour, I decided to give a conceptual introduction, also, of course, with a personal focus. So many topics are left out in this short time, but I hope it will be a coherent presentation. Now, there are four sections, so I divide up the problem of time into a classical and a quantum version. So this is problem of time 1 and 2. Then I say something about a recovery of semi-classical time, semi-classical gravity, and decoherence, the word that has just been alluded to in the last question, because this is related indirectly to the problem of time. And finally, I say something about the arrow of time, which is the origin of irreversibility in our universe? Can we understand it from quantum gravity? Now, it's always good to start with a quote by Einstein, and I had selected the following one. He wrote a foreword to Max Jammer's book on the concept of space. So it's about space, but it also refers on time. And in the English translation, here's the original in German. It took a lot of struggle to arrive at the concept of independent and absolute space and time. This is, of course, what Newton did, which is indispensable for the theoretical development. Otherwise, I mean, he could not have constructed the gravitational law. And it has taken no less struggle to overcome this concept afterwards. There, Einstein refers to himself, of course, to 1905. And then he writes a process that is probably by no means finished. And this, at least, we can allude to quantum gravity and the discussion of time in quantum gravity. So you all know that general relativity is still our best, experimentally best theory of gravity, and the Einstein field equations that he presented first on that date, of course the cosmological constant 2 years later, give this very intricate connection between matter, energy, and space-time curvature. So on the left we have the geometry, the gravitational field, on the right the matter field. So far these are the fields in the standard model of particle physics. Now, a problem of time 1 is also called background independence. No? So we know from classical mechanics, from Newton's absolute space and time, and also from the Minkowski space-time or special relativity, there's a fixed background. Fixed means non-dynamical. It's just a stage, and the fields are dynamical. They are the actors on that stage. Now, in general relativity, this is no longer the case. There is no fixed background anymore. I mean, the stage becomes part of the actors. And this is what is background independence. So if you then later try to quantize, you can no longer do what we do in standard particle physics, quantize on a background. And it was clear, I mean, from the first talk, what are the challenges in doing this, right? So Einstein once wrote, it is contrary to the scientific mode of understanding to postulate a thing that acts but which cannot be acted upon. No? So like the old absolute space-time, which is there, which cannot be acted upon, although it can act. So there are no absolute fields in general relativity. There's no background structure. Now, to see this more clearly and in more detail, I think it's most convenient to go to the canonical formalism of general relativity, to which I restrict myself here in this brief presentation, in the metric formalism. And so we go from the Lagrangian to a Hamiltonian formalism, and this was already done very early. The earliest paper I know on this Hamiltonian is by Felix Klein in 1918, so relatively short after Einstein's pioneering paper. So to summarize, Einstein's equation can be written as a dynamical system, and it's a dynamical system for the 3 metric called HAB here, and its canonical momentum pi AB on a space-like hypersurface that I call sigma of evolution equations, which are not written down here. So the 10 Einstein field equations that you saw earlier are split into 6 evolution equations, and these are on display here, 4 constraints. With 4, I mean 4 local constraints. 4 times infinity cubed, if you like, at each space point. And they are called the Hamiltonian and the Hamiltonian constraint and the 3 momentum constraints. Okay, so they have here this kinetic part and this potential part. And this is from the right-hand side of the Einstein equation from the T-minus, the matter part. And so HAB is the 3-dimensional metric. H is its determinant. This is the 3-dimensional Ricci scalar, the energy density of matter. And here you have the canonical momentum of the attributed to the 3 metric, which is constructed out of the second fundamental form. That is classically how the 3 metric is embedded into the 4th dimension. GABC is the de Wit metric, which is written here, but which I don't go into details. It's a metric on the space of metrics, or the metric on configuration space. Kappa is 8 pi g over c to the 4. So these, in a sense, encode all the structure and all the dynamics of general relativity. And this is brought, I mean, to explicit light by understanding the connection between the constraints and evolution. Now, I've tried to summarize this on this transparency, giving the so-called interconnection theorems. Now, first is the constraints are preserved in time. And time means they are valid on each spatial hypersurface if and only if the energy momentum tense of matter has vanishing covariant divergence. So this gives you a direct interaction relation between, I mean, a very important relation for matter, this covariant conversation law, and gravity. So in electrodynamics, you have a similar theorem. The Gauss constraint, nabla E is 4 pi rho, is preserved in time if and only if there's charge conservation. Now the second theorem states that, okay, if you have these 3-dimensional hypersurfaces, and if you demand the constraints to be valid there, then the connection between separate hypersurfaces has to be done by Einstein's evolution equations, by the remaining 6 equations. And so you don't have to postulate the extra 6 equations if you demand that the constraints be valid on each and every hypersurface. So Einstein equations are in fact a unique propagation law consistent with the constraints. Now in electrodynamics we have a similar statement that Maxwell's equations are the unique propagation law consistent with Gauss constraint, nabla E is 4 pi rho. So this makes it also plausible why in the quantum theory, in principle you only need a constraint and you don't have to deal with the evolution equation. If you restrict to compact 3 space, I don't talk about the boundary terms of asymptotic flat space-time here, then we can say that the total Hamiltonian is a combination of pure constraints, and all the evolution in this sense just said is be generated by the constraints. There's no external time parameter anymore because all there is space-time, and all physical time parameters are to be constructed from within the system that is as function of the canonical variables HAB and P psi D. A priori, there's no preferred choice of such an intrinsic time parameter. Now, the absence of an extrinsic time and the non-preference of an intrinsic one is known as the classical version of the problem of time. But still, space-time exists. Now comes the quantization, and I restrict myself in this short time to the quantization of these canonical equations in metric variables. There's much to say, of course, about this in other approaches, such as loop or string theory. Now, John Wheeler and Bryce DeWitt in the 1960s, after, of course, earlier work by Dirac and the Bergman group and ATM, they presented and, of course, discussed the quantum version of the constraints. And as I emphasized, all there is in the constraints. And so we have this H psi equals 0 and HA psi equals 0. So that's the standard quantization. I can say much about this, but time does not permit. So you have here from the pi ABs, the second derivatives, that you have the de Wit metric and the potential term. And this is called the Wheeler-DeWitt equation. And the quantization of the 3 other local constraints, this leads to the quantum diffeomorphism or momentum constraints, here which look very simple, and this looks more complicated. I don't talk here about the issues of factor ordering and so on. Now John Wheeler on the blackboard, and he was famous for his blackboard talks, that also I remember to have seen one live. What is the difference between the classical and the quantum in the particle case and in the gravity case? And this is summarized here in this table that perhaps you recognize from Misnerson and Wheeler, whose 50th anniversary we celebrated recently, but in a review with Patrick Peter from Paris, in a review on time, we modified this a bit according to our own taste. So here you see the underlying motion. Geometrodynamics, this is John Wheeler's word for Einstein's theory for general relativity, and particle dynamics. So particle corresponds to space, the events to 3 geometry. Now, what is a trajectory in mechanics becomes then a 4 geometry in gravity, HIT from T. Here space-time actually corresponds here to superspace, the space of all 3-dimensional geometries, which is actually the configuration space, and which is the space, of course, infinite-dimensional space on which then the wave functional of quantum gravity lives. So there is no additional time. Now here you have an additional time because in classical mechanics you have this external time in addition to the trajectory, and then you quantize, the trajectory is gone, the wave function remains, but absolute time is of course still there. Whereas here there is no space-time and absolute time in addition. So if you quantize space-time, everything is in here in the 3 geometry. Now this leads to the problem of time 2, or the quantum version of the problem of time, that the space-time has vanished from the formalism in the same way as the trajectory of the electrons, say, and atoms have vanished in quantum mechanics, and only space remains. And this holds for also for loop quantum gravity, and probably also for string theory, although on the latter a more subtle discussion is needed. And perhaps we will hear about that later this week. It's not special now or for quantum relativity. It holds for any theory that classically is reparameterization invariant. That is, for any theory that classically has no absolute time in addition to space-time. Now the Wheeler-DeWitt equation has the structure of a wave equation. So if you look more carefully into this object, it has 1 minus and a lot of pluses. So it looks like for an oscillating string, a wave equation. So you can define, just from the structure of the wave equation, out of the 3 metric, an intrinsic time. Now the Hilbert space structure in quantum mechanics is connected with the, as already Pauli has discussed, with the probability interpretation, and especially with unitarity, so probability conservation in time. So of course the question is what happens with that, and in particular with the notion of unitarity in a timeless situation. Now, I fear, of course, that I run into a problem of seminar time, so I have not included here this kind of the relational observables, because there will also be talks about later. So, so sorry for that restriction in time. But I will mention that this is just a cartoon for the absence of time in quantum gravity. Now, the full Wheeler-DeWitt equation is, of course, complicated, but you can, and this is what is commonly used, discuss it without mathematical ambiguities for finite dimensional systems. And this is the realm of quantum cosmology. So if you consider here a closed Friedmann-Lemaitre universe with the scale factor A containing a homogeneous massive scalar field phi, which is a 2-dimensional so-called mini superspace that Charles Misner coined in 1969. So with the classical line element here written down here, and the Wheeler-DeWitt equation in a convenient choice of units written down here. So you see the kinetic term, you see this hyperbolic indefinite structure. Here the derivatives with respect to the scale factor, the size of the universe A, the field, and the potential term. And out of the 3 metric and the matter fields, only 2 degrees of freedom remain, the scale factor A and the field phi, which is homogeneous. And this is certainly an equation that you can discuss consistently either in some cases analytically or in most cases numerically. Now for the topic time, there is one important issue which is I tried to illustrate here on that picture, namely there is a different concept of determinism in classical and quantum theory. Now the classical configuration space is A phi, and if you have a recollapsing model of a universe, you can, for example, give here initial conditions, have a maximum and recollapse. Of course, you can also start here because you just have the trajectory, there's no direction. So in this sense, the recollapsing part is the deterministic success of the expanding part. But in the quantum version, the trajectory is gone. You have a hyperbolic equation, and for a hyperbolic equation, you give as initial conditions the psi at A, and also its derivative, A equals constant. That is, if you want to construct a wave packet here, following this, then you have to put the wave packet here and here, because A equals constant is the initial value region for the wave equation. Now you don't have the trajectory. And so, in a sense, the recollapsing wave packet must be present initially with respect to A. And if you do not do that, you get a very weird solution and certainly not wave packet. So in a sense, there's no intrinsic difference between Big Bang and Big Crunch in quantum gravity. Now, some time ago, I discussed wave packets, and for example, for this equation, this is the indefinite oscillator. It comes from coupling a Friedmann universe with a conformally coupled field and rescaling. But the point is, it's the so-called indefinite oscillator, as simplest as you can have, like the harmonic oscillator in quantum mechanics. And then you really classically, you have Lissajous ellipses. And if you construct a wave packet, you see here superposition of these Lissajous ellipses. But you have to really put here these two initial conditions here, the two wave packets, the one from, if you like, the Big Bang and the one from the Big Crunch. Otherwise, you get just a mess. Now, in 1919, I gave a talk actually in front of John Wheeler and Bryce DeWitt in Santa Fe, and Bryce DeWitt was very happy that I have here this boundary condition for the classically forbidden region, psi going to 0 as in quantum mechanics, because at that time, I mean, the no-boundary proposal was very popular, but it gives solutions exponentially increasing into the classically forbidden region, which DeWitt was absolutely not amused by, to have this in contrary to quantum mechanics. So you can construct solutions that fulfill classically forbidden going down. So later, actually, the year thereafter, I showed that in the no-boundary proposal, actually these solutions cannot be found from the path integral by going through all types of contours, because the solutions either diverge at infinity or at the light cone in mini-superspace. Now, Chairman has time under control, probably started a bit later, I think. So, of course, from this timeless situation, you should at least be able to recover semi-classical time. And I only have it here in text. No? So if you expand the Wheeler-DeWitt equation with respect to the Planck mass, you get a functional Schrödinger equation for the non-gravitational fields. And in a space-time, that is a solution of Einstein equation. So you can recover, but in an approximation only, the time of classical Einstein theory, with all its covariance, of course. And this is also called WKB time, and the approximation scheme is a Born-Oppenheimer type of approximation, where you can then get the usual Hilbert wave structure and its associated probability interpretation. And maybe the first paper doing it was Lapchinsky and Rubakov's paper in 1979. And also some other work in the 80s. Okay, then you get a pointer at least, but not yet a direction. Now, we thought about then going beyond that and having maybe quantum gravity corrections to this functional Schrödinger equation. And actually, the next order gives a functional Schrödinger equation with the WKB time, but with the matter-Hamiltonian supplemented by 1 over Planck mass squared corrections that I did not write down. So with T.B. Singh from the Tata Institute, we did this, and later with Andrei Bawinsky from the Lebedev Institute, we translated these correction terms into covariant Feynman diagrammatic language. Now, of course, interesting is whether you can observe these things and arrive at a quantum gravity prediction and confirmation. For example, it contributes to the cosmic microwave background. So does the anisotropy spectrum of the cosmic microwave background radiation contain information about quantum gravity? And here again, I don't give you the details. Also, it's not directly related to the topic, but I refer to our recent review with Leonardo Chatenier and Paolo Muniz and all the references. And also Leonardo has a poster here. Also, I think there is about the relational observables where you can also find this, and also the connection to observations. In a sense, one could also say that some quantum gravity effects have already been observed, because even without these corrections, what they usually do in this context and having an inflationary model is to use these Mukhanov-Sasaki variables, which include which then quantize these, and this includes already a quantization of the metric at a linear level. And then you get the power spectrum, which is proportional to Planck time times Hubble parameter squared, which you could say is a test of linearized quantum gravity. But here would be beyond that. Now decoherence, which was mentioned. What is decoherence? Decoherence is the irreversible emergence of classical properties by interaction with environment, and is something that has been discussed long ago in quantum mechanics. And so I transfer this also to gravity. But okay, what is their system? What is their environment? And it was suggested that system, these are the global degrees of freedom, such as a scale factor, and the environment are small density fluctuations, such as tiny gravitational waves. Environment does not mean something outside the universe. Everything here happens in configuration space. So the configuration space of all variables is divided up into relevant and irrelevant part. And for example, one example that we discussed with Bawinsky and Kamenschik was that we have this semi-classical de Sitter universe inflation, and that we have decoherence by the interaction with gravitons, with small unobservable gravitational waves, so that the local density matrix gets modified by having here this suppression of non-diagonal terms in this way, which means that the superpositions that you have here, of course, in quantum gravity, say with different scale factors, gets suppressed. So the universe also assumes classical properties at the beginning of inflation, and time, in a sense, can also be understood, or the emergence of classical time by this decoherence or by symmetry breaking, because to arrive at semi-classical WKB time, you have to have an e to the is state for the gravitational field. Now you could also add the e to the minus is to arrive at a 1 minute, okay? This is the real problem of time. And so in a sense, there's also this analogy with sugar molecules, where we have the parity invariant Schrödinger equation, but you have parity non-invariant states, such as chiral sugar states, and they become decohered through interaction with photons, optical activity. And here, of course, you have then e to the is and e to the minus is, and this decoherence between the two can be done, for example, with weak gravitational waves that has also calculated. Yeah, okay, then maybe I skip then the last part of the arrow of time, unless someone asked in the discussion session. It's only 2 slides, but I just mentioned this decoherence of the primordial fluctuations, because they are quantum fluctuations, as I as I emphasized, both the metric and the inflaton field. But this degreeness is also important because to serve as classical seeds for structure formation, they need to be classical. And this is also done with Polarski and Starobinski we discussed some time ago. And yeah, okay, I skip the error of time and leave you with that picture. So these are the decohered quantum fluctuations of the early universe. So thank you very much.
So thank you a lot for this.
Yeah,
very
time
nice
runs too quickly, I must say.
Yeah, time is heavily running here in Nijmegen. Are there questions? Yes, please.
Klaus, thank you for a very nice talk. The work that you did with Paolo Moniz that you mentioned in passing, that you can actually see quantum features in the anisotropy of the background radiation. You mentioned that when you see stochastic behavior, it's a strong indication that it is quantum. I just want to comment, I don't know whether that's what you really meant, but there's a big gap between quantum and stochastic. And in fact, in the literature, people usually say we'll do quantum cosmology or quantum mechanics, but let's assume that it could be substituted by a stochastic classical source. And that's a big mistake usually. I'm not saying that you're doing that.
No,
I just want to clarify.
I fully agree with you, and it's just not done that because what we did, I mean, there's nothing to write here, but well, maybe otherwise I would start giving a lecture. But yeah, no, that's you have this Schrödinger functional Schrödinger equation, which is a Schrödinger picture analog of quantum fields in curved space-time. This you recover as an approximation, and then to this wave function you get really quantum corrections 1 over mp squared, and this stochastic behavior here only comes then after you take into account the coherence, and so it's not put in at a fundamental level. So it's really, yeah, like for example, if you take the Dirac equation and you recover that in a 1 over c squared approximation, the Schrödinger equation and this Foldy-Wutthuysen transformation, and then you get 1 over c squared corrections to that. That's the analog to that. So really quantum and not stochastic.
The quantum features, yeah.
Yes, can you say something about the older definition of the problem of time variable in canonical quantum gravity, where it was defined as finding a canonical transformation such that your Euler-de Witt equation is transformed into Schrödinger equation, effectively?
Oh, yeah. I could also say that. You mean the reduced approach, right?
Yes, if you fix the time in the end.
Yeah, I of course had to exclude all of this here in this very short time. This is what, there's just nothing to write. So, I mean, you can, well, just what you have this classical h equal to 0, then this would mean to classically reformulate to identify a time, because you have this ambivalence of choosing many and write it in the form pt plus h reduced equals 0. No? And if you have this pt plus h reduced equals 0, you can then write the pi t transformed to h power over I t over dt, and the h reduced to h operator reduced. And then you have a Schrödinger equation. No? And that's the reduced approach that has been followed from the very beginning. In particular, Karel Kuchasz has done a lot of important work on it. The point is, I mean, he also proved various theorems, various no-go theorems that you cannot globally do that. Yeah, so it prevents, I think, also by Torre, Charles Torre has theorems of 93. And even for those cases where you can, it's very hard to do explicitly, because typically you get this h reduced as some square root terms, say square root of momentum squared plus a complicated functional of q. And so you have to quantize this square root. And it does not take very long, then you are stuck with that. So this is maybe a short answer to that. But in principle, of course, that's a valid alternative to think about.
Yeah, one brief question by Sumati, and I think then we have to break for coffee.
Yeah, this is a general question, but about these, here you talk about gravitons helping decohere. Of course, the whole system, I mean, it's a single system, it's a closed system, but you're choosing to divide into things that, you know, in something like Born-Oppenheimer you might want to do. So are there scales involved in here when you do such a decoherence, which allow you to treat one part of it as system and one part of it? So in other words, what uniquely determines that division? This is sort of...
Yeah, good question. This is, of course, at the center of this decoherence approach, and there is no God-given unique division, because you divide up into relevant and irrelevant degrees of freedom. And if you think about quantum mechanical examples, then what is relevant and what is irrelevant can differ from one case to each other, right? If I want to have, say, if I have an interference term, an interference experiment, for example, the ones that have been done in Vienna with Buckminster fullerenes going through interferometers and producing interference patterns, they discuss decoherence in two ways. First, they have a vacuum, but they introduced a gas into that. And then the gas was the environment that decohered the interference of the Buckminster fullerenes. But in other experiments, they just heated up the fullerenes, and this led to emission of photons. So in that case, actually, this environment came from the system itself, in a sense. Yeah, but the point was it emitted photons that were no longer under scrutiny, that you could not observe. No? So in a sense, in quantum mechanics, it's up to the genuity of the experimenter to really know what is relevant, irrelevant. So you already should have an idea about, say, what is your system and what is composed of. If you don't know this before, then it's hard, if not impossible, to discuss decoherence. If you just have the full quantum world with everything quantum, then everything is quantum. So you have to somehow zoom in and know what is system and environment. And of course, then is the issue with the pointer basis. What is the classical basis? And this is again then given by, say, your Hamiltonian that you write down. And of course, this has to be given. Your physical theory, your physical degrees of freedom, and your Hamiltonian should be there. And then, given on a situation, you have to point out, not here, this is not under control, this is irrelevant. Say, like in these examples, the small gravitational waves that are all around here, but that we cannot measure, are the environment. Yeah.
So, thank you. And then I have a brief announcement. So coffee is, if you go outside of this lecture hall, in the Kulturcafé. So probably the locals can guide the way. So it's in this building, but you have to walk like 20 meters. Okay, good morning and welcome back everybody to the second session on this Monday morning. Before I get started, there are two announcements. The first announcement is here in this building there are also exams going on. So please use the coffee area for discussion and not the corridors. The students will certainly appreciate this. Secondly, it came around people asking for the quality of water here in this building. So all water that you can get from the tap in the Netherlands is drinkable. It's phenomenal. You don't need to rely on bottled water. Otherwise, the Kulturcafé and the lunch area will serve bottled water. At this point, it's then a great pleasure to introduce the review speaker of the session, Ignatius Antoniadis. So if you check his Wikipedia entry, it says he's a Greek theoretical physicist working on string theory and particle physics. So I think this is a bold understatement. So basically he has worked on every topic related to particle physics and string theory. And since there is a lot of young people here in the audience, I want to share a personal experience that I had with Ignatius about 20 years ago when I was a young PhD student. So we were working on a problem related to geometry, and we had a problem in getting it reconciled with one of his works. And then there was CERN school, you knock on the door, and you ask, do you have 5 minutes? And happily he said, yes, I have 5 minutes. Then I was explaining him this and this is the computation. And then he went to his drawer saying, this is what we did in terms of computations for this particular paper. And within 2 minutes, we have figured out what was bothering me for, I think, at least 3 months at this point. So for the young people, take the message, be bold, approach senior guys. And for the senior guys, please be bold, take the time to listen to these young students. You never know where they will end up. So this said, I'm very happy to give the floor to Ignatius and his talk. Thank you.
Thank you very much for the invitation and for the introduction. I was asked to make a review on string theory, so I choose this topic, which will be also an introduction to the focus talk and also I think more appropriate for this audience. So a challenge for the fundamental theory of nature, such as supposed to be a string theory, is to describe both particle physics and cosmology, so phenomena at very short distances as studied in accelerator experiments, and phenomena observations in the universe. And we know that both offer a complementary information for the same underlying theory. The first puzzle when we compare the two observations, the two data, is that the content of the universe, as we learn from observations of the sky, it doesn't seem to overlap with content of standard model of particle physics, which is only a small fraction of it, and most of them, the remaining part is unknown. It has the names dark energy and dark matter. So since it will be relevant for my talk, the dark matter, as we know, describes about 70% of the observable universe, and can be described by a fluid with negative pressure equal to the density. And the simplest explanation is a cosmological constant, which when we put on the other side, on the right-hand side of the equation of motion, one obtains this equation of state. There are two length scales associated to the cosmological constant. One is classical, because it has a dimension of length to the -2, classical dimension, as the curvature. And this can be deduced from the observations. It's essentially the size of the observable universe from the measure of the Hubble parameter, and it is 10 to the 26 meters. On the other hand, if we see it as a dark energy, one has to infer it from the energy density, so you have to divide by the Newton constant, and then to infer a length scale, one has to use the quantum Planck constant, and then we find this a length to the -4, which is associated to the dark energy length, which is very different from this one. It's much bigger. It's about 85 micrometers. This is curiously enough close to the present bound on the validity of Newton's law at short distances, which is about 30 micrometers. And this is due to Eötvös experiment in Washington by the group of Adelberger using this type of device. Going back to the challenges of a fundamental theory of nature, one of the main issues to understand is the problem of scales. Yeah. So I put the scales here. We have somewhere here the scale of quantum gravity that we heard already about today. Here is the scale of particle physics of the standard model, about 100 GeV. And this is the scale of dark energy, this 85 micrometers, which in energy scale is milli-electron volt. Then there are two scales that one comes from particle physics and another from cosmology, but they are not established. We don't know if they exist, but they are introduced by many theories, and they are likely to be there. One is the scales from youth physics beyond the standard model, and one possible idea is supersymmetry, which has not been discovered in accelerators, but it can be anywhere between the electroweak scale and the Planck scale. And the other scale comes from inflation, which describes another accelerating phase of the universe, but with much different value of vacuum energy than the dark energy today. And again, this can be anywhere here. So I will discuss essentially the framework of string theory, and one of the ingredients of a consistency of string theory is extra dimensions. They are formulated in higher dimensions, in 10 dimensions. In 10 dimensions, there is an extra parameter apart from the length scale, so the string length. Is a string coupling, but the string coupling can also be treated as an extra dimension starting from one dimension higher, which is called M theory, 11 dimensions. So by this, I want to say that the main ingredient of consistency of string theory is extra dimensions, including the string coupling, which controls the quantum corrections in string perturbation theory. The second ingredient is that matter and gauge interactions, so our universe in particular, could be localized in lower dimensions, can form a brane, as it is called, a hypersurface, three-dimensional hypersurface that moves with time. And this makes immediately opens the possibility that the dimensions which are the remaining of the dimensions which are transverse to the brane can be large. By large mean larger than micron or 30 microns that was bound of the Newton's constant. And this allows the string scale to be dissociated from the four-dimensional Planck mass and become lower anywhere in this energy range, like these two scales. So there was a new way to address physics problems scales using this possibility of having low string scale. For instance, it can be as low as the multi-TV region to explain the electroweak hierarchy, or it can be at some intermediate energies, which could be associated to, for instance, the supersymmetry breaking scale, the strong CP scale of axion, neutrino mass scale, and so on. As I said, in higher dimensions, the theory looks like it has no parameter other than the scale. The parameters arise by the compactification of the extra dimensions to 4. And these parameters are dynamical because they can be expressed as an expectation value of scalar fields from the point of view of the 4 dimensions, which have no potential, and they are called moduli fields. So for a long time, it was believed that once we will be able to find a way to induce a potential for these fields, then would be able to determine the vacuum and therefore compute the low LZ couplings and other observables. However, with the present knowledge that we now know at least a particular way of introducing potential for these fields and fix their expectation values in a controllable way, it turns out that these parameters are fixed in terms of some discrete parameters, which the theory has, and which are generalizations of magnetic fields, but in the internal dimensions, but not for gauge fields, but for higher rank tensors that come from the theory in higher dimensions, and were called discrete fluxes. There is essentially a huge number of such discrete parameters, and the compactification parameters are fixed in terms of those. So the stabilization of the moduli in this way gave to a huge landscape of vacua. This is what I say landscape, and in a sense didn't much help to determine which vacuum could describe our universe. So this implied in particular that we realized that one needs an extra input or a guidance principle to look into this landscape of vacua and locate where our universe could be there. So that is that part, and now I'm coming to the swampland program, which to my view, it may provide such a guidance principle. So this program started by Kumru Vafa about 20 years ago, and the observation is that not all effective field theories can consistently couple to gravity, although they could be anomaly free, for instance, which is one of the conditions. By many examples, one can realize, convince oneself that a consistent ultraviolet completion of effective field theories can bring more trivial constraints when it is possible to couple to gravity or obtain from a compactification of string theory. So the string theories which are not, the field theories which are not, cannot be consistently coupled to gravity, they're called that they form the swampland, as opposed to the landscape. And of course, there are no exact proofs. There are criteria which are based on conjectures, and these conjectures are supported by arguments which are based on black hole physics and on the current knowledge of string theory. So these are some well-established examples. So the idea, for instance, we know that there are no global symmetries in nature because they're connected to the no-hair theorem of black holes. Or another example is what is called the weak gravity conjecture, which is a statement that the gravity is the weakest force of nature. And it implies that there is a non-minimal, a minimal non-trivial charge, which has to be bigger than the mass of a charged particle in Planck units. In some sense, this conjecture is related to the absence of global symmetries, because if one starts with a local electromagnetism, tune the coupling to 0, then one obtains a global symmetry, which is forbidden. So the question is qualitative, how small the coupling can be, and this is where this weak gravity conjecture enters. Tells that it cannot be 0, it has to be bigger than the lightest, than the mass of the particle. Now, in the rest of my talk, I will describe a particular, it will be based on another Swampland conjecture, which is called distance or duality conjecture, and which states the following statement, that at large distance in the field space, in this landscape of Acua, there is a tower of exponentially light states with a mass which fall off exponentially within the proper distance, with an exponent which is of order 1 parameter in Planck units. So this this means you have the landscape of Acua and field that I described before. The natural, let's say, region of the landscape are theories in which parameters are of order the Planck scale. This statement is a statement about how what happens when you look at corners in the landscape where you have the large distances. So that is the statement, is that there is an exponentially tower of exponentially light states, and this tower provides a weakly coupled description to the theory, up to the effective field theory, up to a scale which is called species scale, and which is essentially a scale where gravity becomes strong. And this was introduced by Dvali back in 2007. So M star is the distance, is the species scale, which is the scale where the gravity becomes strong. And if you have many degrees of freedom, then this scale is lower than the Planck mass by the square root of the number of species, numbers of particles. And so by species means particles whose width is less than their mass. So these are two examples for this tower. One example is the Kaluza-Klein tower, which is associated to a decompactification of extra dimensions, which are part of string theory. In that case, the species scale is just corresponds to the gravity scale in higher dimensions. If you have d extra dimensions in 4 plus d extra dimensions, which is related by this condition, which is essentially the Gauss law of gravity in higher dimensions. So small m here is the compactification scale, 1 over r, let's say the size of the extra dimensions. And the distance, the proper distance, is the logarithm of the radius in 4-dimensional Planck units. So this is important to understand that the linear trajectory, Kaluza-Klein trajectory associated to the extra momentum, which is discrete when a space is compact, actually corresponds to an exponential decrease of states, of masses, in terms of the proper distance, where the proper distance is the logarithm of the radius. And this can be, for instance, seen in this simple example just by looking at the compactification from, let's say, 5 to 4 dimensions, or from any higher dimension to lower dimensions. A second example is a tower of string excitations, which is contrary to Kaluza-Klein tower, which contains exactly powers of the same spin as the lower mode, but with higher masses. This contains particles with increasing spin with the mass. In that case, the species scale is associated to the string scale, which is proportional to the Planck mass with a proportionality factor, which is a string coupling. But the string coupling, as I said before, is associated also to an extra radius, and the associated distance, the proper distance, is the logarithm of the string coupling, and therefore it obeys this rule. By an analysis of possible large distance exploration in the compactification of string theory, it was argued that these are, by these people, it was argued that these are the only two possibilities that one can have. Now I come to the main statement, which is a statement now about physics, is that it can be that the smallest of the proposal, if you want, is that the smallest of some of the physical parameters that we have in our theories, it could be a manifestation that we live in a large distance of the corner of the landscape. So I will try to elaborate on this. First of all, an early example of this statement, of this proposal, was back in '88 when the first string compactifications have been analyzed and explicit four-dimensional strings were constructed. It was observed at that time that if one finds a four-dimensional vacuum in which you have a state which has the quantum numbers of a spin 3/2 particle, like a gravitino, which is a partner of under supersymmetry of the graviton, which has a mass much less than the Planck mass or the string scale, then the rules of the consistency of the rules of the construction imply that there is a tower of states which have the same quantum number and masses, but at higher masses on top of this lower line state. So here K is an integer, which is the tower, 1, 2, 3, and so on, so like a Kaluza-Klein tower. And capital N is another integer, which is not too large, and one was able to bound it. For instance, in constructions using free fermions on the world sheet of the string, this capital N was less than 10, while using bosonic bosons instead of fermions, was able to bound it around 1,000. So this relation actually can be written in this way, which I will use it later on in a different context. So M is the mass, the characterized mass of the tower. So in this case, like a Kaluza-Klein tower. M 3/2 is the mass of the gravitino, so the supersymmetry breaking scale. And this lambda is some proportionality factor, which is not too big. In that case, is 1/n, which is this one here. So more recently, about 2 years ago, there was a proposal, actually 1 year ago, it was a proposal by the group of Wafa at Harvard that the dark energy could be, or the cosmological constant, if you want, could be associated precisely to which is a small parameter in Planck units, could be associated to the fact that our universe lives in a large distance in the landscape of vacuum, in the landscape. And there is a tower of states which are exponentially light associated to the cosmological constant with a power like this. In other words, in Planck units, the m is the mass of the tower, so the lowest state, and lambda is the cosmological constant in Planck units, say some parameter. So this is like the relation that I wrote here, but it's not linear. It has some exponent a. And this exponent is bounded between 1/4 and 1/2. Now, the first ingredient under which this proposal was made is that the proper distance is the logarithm of the cosmological constant and in the field space. And this was proven for added de Sitter vacuum. So when the cosmological constant is negative, it was assumed that it is also valid in the case where the cosmological constant is positive. That is the basic assumption here. Now, about the bounds, the 1/2, so the upper bound for the exponent comes from unitarity. It is associated with the so-called Higuchi bound, which was an observation back in '87, that in the Sitter space, when you have a massive spin 2, the unitarity implies that the mass of any spin 2 must be bigger than the horizon, the Hubble scale. So it's a square root of the cosmological constant in Planck units, and this is how the 1/2 arrives here. Otherwise, you have negative norm states. The lower bound is an estimate that once you have a mass scale m, then there is a contribution to the vacuum energy, which goes like m to the 4th by dimensional analysis. So unless there are spatial cancellations, there are corrections of the order to the vacuum energy of order m to the 4, and this is how the 1/4 arises there. So this is from the theoretical input, of course, using this proposal that the small parameter could be related to the fact that you have large distance in the landscape. And then one can introduce the constraint from observation. So we know that lambda is 10 to the minus 120 in Planck units. That this mass scale cannot be smaller than 30 microns, so 0.01 electron volt from the Newton's law, which imply both of them that the power here is essentially 1/4. And once you have one extra dimension at the micron scale, then necessarily you cannot have more than one extra dimensions because there are astrophysics bounds from supercooling of the supernova. And this determines, so the input from observations imply that if this is true, then there is one extra dimension at the micron scale, and therefore the five-dimensional Planck scale, which is the species scale, is lower than the Planck scale to a value of the order of 10 to the 8, 10 to the 9 ZeV. There is still this parameter here that I said before in that example. It was between 10 and 10 to minus 3. Similar bound can be obtained here. The upper bound essentially comes from the Newton's law, and the lower bound is a heuristic statement that if lambda is too small, then it's essentially you can absorb it by changing the power A. And obviously, this scale cannot be a string tower, so it has to be a Kaluza-Klein tower. What is nice about this proposal is that it has immediate physics applications, which I mentioned here. So one application is that it can realize an old idea in the context of large extra dimensions, that can provide the fact that you have an extra dimension at the micron scale can provide a natural explanation for the neutrino masses by identifying the right-hand neutrino as a state that propagates in the bulk, that propagates in 5 dimensions. Obviously, the standard model should be on a brane which is localized in that dark dimension, as it is called. And using the recent the neutrino oscillation data, one finds that this compactification scale should be bigger than a few electron volts, which means that this this coefficient is about 10 to the minus 3, and the species scale, or the 5-dimensional Planck scale, is about 10 to the 9 GeV. Second application is on that it provides 2 new candidates for dark matter. The first is to be 5-dimensional primordial black holes. I call them 5-dimensional because their Schwarzschild radius is smaller than the micron scale, which is the length of the extra dimension, and therefore they behave like 5-dimensional. And as a consequence, one can see easily that a black hole, a 5-dimensional black hole, if you compare it with a 4-dimensional one with the same mass, lives longer, and therefore it allows to bypass the bounds on primordial black holes for being dark matter that come from the black hole evaporation. This is for the low mass region. These are for 4-dimensional primordial black holes. The possibility to describe 100% dark matter. So they can be either lower than about 10 to the 22 grams. Here the bound comes from microlensing, and the lower bound was coming from evaporation, but if the black hole becomes, as I mentioned, 5-dimensional, then it lives longer, and then this bound is not there, and the range is extended by about 3 orders of magnitude in the lower mass region. Another possibility is that dark matter could be identified with a Kaluza-Klein excitations of the graviton, which lives in 5 dimensions, and which have a decrease in mass due to the internal decays. The Kaluza-Klein excitations are decaying in the lowest, I mean, from higher mass to lower mass, and by choosing appropriate the rate of decay, one can provide an explicit realization of the proposal of dynamical dark matter, which means that the mass of the dark matter changes with the temperature, starting from about MeV at the matter radiation equality, and it becomes about 50 keV today. So this can be realized by this proposal. Actually, there is a choice of the parameters in which the 2 possibilities give the same observable effect. And in order with the black holes to describe the lowering of the mass of the dark matter, one has to introduce the possibility that the black holes accrete from the medium and become, and therefore you obtain the same result. The next question is, what about inflation? If the four-dimensional inflation occurs for fixed radius, if the radius of the extra dimension, which is about the micron, was stabilized at the time of inflation, then this implies that there are spin 2 excitations which have a mass at the electron volt range, and the Higuchi bound that I mentioned before implies a bound for the Hubble constant now of the inflation, which is translated to a bound on the scale of inflation to be less than about 100 GeV. This, in principle, could be, I mean, there's nothing wrong about this, to have low-scale inflation. But there is another interesting possibility that inflation arises in 5 dimensions and the extra dimension expands with time. What is interesting about this is that one could try to, by this way, one can try to relate the hierarchy that one needs from the extra dimension to become large at the micron scale, starting from the fundamental scale, which is 10 to the 9 GeV inverse. This requires expansion in the of the internal dimension of about 42 e-folds. And if we compare, so starting with the 5-dimensional inflation, which is the Sitter space with some scale factor here, A5, starting with a compact dimension, which is which has the size of the fundamental scale of gravity at that time, and compare it with a 4-dimensional space-time, in which the embedding comes in this way. This is in order to normalize the 4-dimensional Planck mass to unity from the 5-dimensional Planck scale that you had before. One finds the relation that the 4-dimensional scale factor grows like 3/2 of the radius factor, which means that 40 e-folds of the radius corresponds to about 60 e-folds in ordinary space. And this is a very nice result because it connects the number of e-folds, the size of the observable universe, if you want, with the size of the extra dimension that makes gravity strong, that makes gravity, weak, and the Planck mass to increase from the fundamental scale, which is 10 to the 9 GeV here, to the Planck scale. If I have time, I may mention how this works, what the physics you obtain about this. Now, the easiest way to do inflation in 5 dimensions is by introducing an inflaton, which is a 5-dimensional field. This inflaton has to couple to the brane so that at the end of inflation, it can decay by oscillations to the standard model fields and populate our universe with ordinary matter. This can be done by introducing a Yukawa-type coupling like the right neutrino that I said before. And this coupling will be suppressed by the volume of the bulk, so by the volume of the extra dimension. If one imposes the condition that the decay to Kaluza-Klein gravitons is suppressed compared to the decay of standard model, so that the decay products are primordially, they're standard model fields, then one obtains a condition that the mass of this inflaton, 5-dimensional inflaton, should be about less than about a TeV, which is fine. Then at the end of deflation, there is a 5-dimensional cosmological constant at the minimum of the potential, which provides a runaway potential for the radion. The radion is the field, the scalar field that corresponds to the fifth component of the metric. And this runaway potential is quintessence-like. In other words, in terms of the normalized field, which is the logarithm of the radius, that's the same, because the same result that I mentioned before. It's the normalized field. It is the one that associates to the proper distance. One obtains a potential, exponential potential of that form with an exponent which is about 0.8, which is just the allowed upper bound for quintessence field. Of course, one could try to stabilize this field by additional contributions, which I can talk if I have time. Another possibility came more recently with the results on the nanograv and other experiments about the stochastic gravitational waves. And an alternative explanation of this signal, if it is correct, is provided by what is called fuzzy dark matter. Fuzzy dark matter consists of ultralight bosonic particles with wave-like behavior at galactic scales. It means for a mass of about 10 to the minus 23 electron volt for these bosonic particles, one obtains a wavelength of about 5 kiloparsec that explain this wave-like behavior at galactic scales. At larger distances than this, the fuzzy dark matter behaves as cold dark matter, but at lower distances is different, and that's why it has this name. Now, the observed signal from the pulse of time in array can be, it's a signal in the time arrival of stochastic sinusoidal oscillations of amplitude 10 to the minus 15 and the frequency of a few nanohertz. So the observation was that similar signal can be produced by such a ultralight bosonic particle of mass 10 to the minus 23 electron volt and using the density of the known density of dark matter. And in fact, the oscillations of this light bosonic field generate fluctuations in the metric perturbations that produce a similar signal that was found. So an interesting possibility here, which gives still another possible candidate for dark matter, is that the radion of this associated to this dark dimension, I call it quasi-stabilized because it may be not exactly at the minimum, but it may be slowly varied, can play the role of this fuzzy dark matter. So in fact, the first observation is that the mass, which is square root, which is proportional to up to the factor to the square root of the cosmological constant, goes precisely in that bulk mass range, and the frequency precisely matches. Of course, one has to make sure that the radion is produced. So in that case, the radion can be produced by the 5-dimensional inflaton decays through the Kaluza-Klein extensions of the gravitons, which now must be unstable. So before, one had to choose the parameter space that these Kaluza-Klein extensions live long enough to be possible to realize the dynamical dark matter. If this is not the case, but this they decay very rapidly. On the contrary, from the previous proposal, one can arrive at the possibility that the whole Kaluza-Klein tower decays to the radion before the QCD phase transition, and therefore the radion is there, and can, with such a mass, and can explain that signal. One can ask also the question, what about the radion coupling to matter? This should be suppressed, otherwise it's like a Brans-Dicke scalar with a big parameter, omega minus 4/3. This was discussed in that old work of Quintensens by using quantum corrections. Alternatively, one can just have introduce a localized kinetic term of the radion with a coefficient zeta here, some parameter which corresponds to a vacuum expectation value of a brane field. So that was parenthesis that I mentioned also as a possibility because of the recent results. Now what I would like to do is, since my time is over, and I will switch, I will skip the, thank you, the gravitino mass conjecture, which is, it's a possibility that the same thing, the same logic that applied for the cosmological constant as a small parameter, you can also try to apply it for the gravitino mass as it was the initial observation. In other words, the smallest, if supersymmetry is realized in nature, the smallest of the scale could be also a manifestation of a large distance in the landscape, which means essentially the decompactification limit. And the interesting property here is that one can relate the tower of states which is responsible for the dark energy with the same tower to be also responsible for the smallness of the gravitino mass and therefore the smallness of the supersymmetry breaking scale if it is realized in nature. But I prefer to skip this part and discuss a little bit about this unpublished work, which will be published soon. I mentioned before this possibility of obtaining large extra dimensions from hard dimension inflation, how it could work in one dimension. Actually, the same mechanism, you can do it in any dimensions, in more than one, starting from a hard dimensional theory to introduce inflation and relate the size of the observable universe with essentially the hierarchy of that explains the weakness of four-dimensional gravity. So starting with a uniform inflation in hard dimensions, so essentially the same thing that I did that I mentioned in 5 dimensions, you can do it in the hard dimensions, and it is easily to be convinced that one can solve the horizon problem for any dimensionality by relating the number of E-fluids in space, in a non-compact space, with a number of E-folds that you need to blow up the extra dimension from the fundamental scale to the scale which associates to the present strength of gravity. What is more interesting, I mean, as a question to ask, is what about how in this scheme you can generate density perturbations? I mean, one of the successful predictions of inflation is that it gives rise to density perturbations, which in accordance with the observations. So one can study the question about whether one can produce density perturbations that you observe in CMB from a higher dimensional inflation. Here one has to, the main point that one has to take it into account is that the physical distance in higher dimensions with the physical distance in 4 dimensions, they are related by this factor that I mentioned before, which is essentially the ratio of the 4-dimensional Planck scale today compared to the higher dimensional, the fundamental length of gravity. Then one can start from of the observation that the present precision of the CMB data for angles less than about 10 degrees, these correspond to distances about megaparsec at the CMB, which means gigaparsec today. Going back in time, the megaparsec corresponds to a million of kilometers if inflation was realized at the TV scale with radiation-dominated universe. This is further decreased if one pushes the inflation scale back from TV to, let's say, higher, to the, some dimension, some scale, of near the scale of fundamental theory M star. And then it has to be converted to the higher dimensional distances by this relation. And one finds a micron scale. In other words, the megaparsec in CMB goes back to micron scale at, in the back, if the inflation happened much before. And this singles out the 1 dimension as the only possibility that this can work. For more than 1 dimension, so one needs to introduce a period of 4-dimensional inflation in order to be able to generate scale invariant perturbation, density perturbations. However, for 5 dimensions, for 5-dimensional inflation, the result is that you, in principle, one can generate, one does not need the 4-dimensional inflation, one can generate also density perturbations consistently with CMB. One can do that explicitly by computing the density perturbations in 5 dimensions in the Sitter space by using 1-dimension compact of radius r. And then one sees two behaviors for small wavelengths or large momenta. Then the amplitude of that one obtains of the power spectrum is constant, corresponding to a spectral index 1, while for larger wavelengths one obtains 1 over k behavior, so it means more power spectrum at large wave lengths, which make the spectral index 0. That means that if one looks at this CMB spectrum, one sees that the errors start around 10 degrees, and this is what you obtain here in by 5-dimensional inflation. So this is the multiple moments less than 10, which correspond to about 10 degrees. That is the spectrum that you obtain from the 5-dimensional inflation versus the scale invariance of if you extrapolates the 4-dimensional result. I guess I'm about to finish. There is some time left over, or not?
I think you can take 2 more minutes if you like.
Yeah. I mean, I can also find a way to stabilize the radion, the modulus field that I mentioned before, using the Casimir energy. So let me go to the conclusions. My message from this talk was that the smallness of some of the physical parameters that we have that we observe in our universe. It may be a manifestation that we live at large distance corner in the string landscape of Aqua. And such parameters can be the scales of dark energy and the supersymmetry breaking scale. There was an interesting proposal based on this which introduced this dark dimension proposal, which is a mesoscopic extra dimension at the micron scale with interesting phenomenology concerning neutrino masses, dark matter, cosmology, and supersymmetry breaking that I tried to give some glimpses of this. I didn't describe a lot, didn't describe much the supersymmetry breaking scale. But I described the possibility that one can obtain large extra dimensions from higher dimensional inflation by connecting the weakness of gravity to the size of the observable universe. And this could give rise to scale invariant density fluctuations from a 5-dimensional inflation, so for one extra dimension. And also one can obtain stabilization of the extra dimension, the field of the radion field that I mentioned before, with a mass that varies in general between the electron volt and 10 to the minus 30 electron volt, which includes that region in which the radion can be fuzzy dark matter that could be related to the signal that was reported of stochastic gravitational waves that reported recently. So, yeah, thank you.
Thank you. Thank you for this nice talk. Are there questions from the audience? Yes, please.
Well, my question will be the following. What do you think about the idea that we can have Lorentz symmetry breaking so that the Lorentz breaking vectors are directed along the extra dimensions? I am asking because such a concept was suggested by Sean Carroll.
Lorentz invariance is broken by...
Yeah.
Here you have an extra dimension, so the 4-dimensional Lorentz invariance is not broken.
No, the extra dimensions.
Yeah, the extra dimension is, in a sense, that Lorentz invariants become discrete. I mean, for instance, if you have toroidal compactification, then the momenta are conserved modulo an integer. And then, okay, it depends on the microscopic theory if this violation of momentum conservation give rise to the decay of essentially the Kaluza-Klein modes. And depending how fast is this decay, you can have these various possibilities that I mentioned. But there is no a priori, how to say, there's no particular prediction. It can vary, it's model dependent, this violation of the momentum conservation.
Yes, please.
So, when you said your fuzzy dark matter proposal already can incorporate the cold dark matter, do you mean that you obtain the equation of state parameter to be 0, or
yes.
Is it an assumption?
Yes, the obtain parameter to be 0.
You obtain it exactly.
Yeah, for wavelength, for distances bigger than the galactic scales, such a light particle behaves like cold dark matter. But for shorter distances, the physics is different. That was
okay, and does that hold for the other dark dimension proposal also? Is there a range of equation of state, or that is also exactly cold dark matter?
No, as I mentioned, it can be embedded in the dark dimension proposal. You have this extra, the dark dimension, and then everything depends on how fast the Kaluza-Klein excitations of the graviton decay. So you start, let's say, if you have 5-dimensional inflation, you have oscillations of the inflaton, they decay to Kaluza-Klein excitations of the graviton, and then those decay to, if they decay fast enough, they will go to the radion, if the radion is very light. Otherwise, it could be they could be, for instance, dynamical dark matter, or
Okay.
you know.
Thank you.
No, he first, then Laurent second.
Oh, is it working? Oh, when you talk about inflation from extra dimension, you said that d equal 1. Additional dimension is 1 is preferred. How do you explain this in the context of string theory? Because you are talking about the string phenomenology.
Yes, in the context of string theory, it means that all the other dimensions are fixed at the microscopic scale, at the fundamental scale, and they are not expanded.
It sounds to me very artificial that you single out only one dimension. How you can explain naturally?
Well, they don't need to be isotropic, all the dimensions. It's,
sure, but there could be 2D extra dimension that which is large, and how you can.
I mean, they could be that the you know, that the other the dimensions which are of the order of the string scale, they are part of our universe in the sense they have a length which is in which the light can propagate. No? So it means, but they are small. They are small. They cannot be big in that case. No?
Okay.
In other words, it depends on what type of brain you have.
We can discuss later.
Yeah.
Thank you.
Yes.
Thanks. It's a question maybe more technical about the beginning of your talk. You mentioned this interesting conjecture which relies on the existence of a metric in field space. So the puzzle I have is that I was always expecting that field space is invariant under diffeomorphism. That is, you can change field space in arbitrary manner. But this conjecture require a particular choice of a metric. So do you have access to, in that conjecture, is there, you know, how do you know which metric on field space to work with, and how is it determined? That would be remarkable if there is a preferred choice there.
This space, first of all, is discrete, right? Because all the internal directions of the metric are fixed in terms of discrete parameters. So you have a huge space, but it's discrete space.
So it's not really field space then?
It is a field space because if you want, the fields have an expectation value which is fixed.
Okay.
So you can define the proper metric because you know what is the field, and you take the field to be a proper. I mean, proper metric, proper distance means that the field is canonically normalized. Take the example of the radius. The proper distance corresponds to to measure distances with the logarithm of the radius, which corresponds to the normalized field.
So you assume that it's a flat metric in field space?
Yeah, you assume flat here. Yeah, you assume flat. Is
that natural? I mean,
it's natural if you require.
We expect field space to be a bit more complicated than that.
I mean, when you compactify your theory from 10 dimensions to 4, then the internal you obtain from the equations of motion that the internal metric has to be flat. Because the 4-dimensional, you want to obtain 4-dimensional Minkowski space. So that's why.
Okay, I'm afraid we have to postpone further questions to the lunch break. So let's thank again for the nice talk. And then it's my great pleasure to introduce the second speaker of this session, Arthur Hebecker. So Arthur is professor at Heidelberg University and specializing in string theory and currently investigating problems to the string landscape. And I have to say that there's a story to this talk, so it will be given virtually. So having had Corona in the past, it felt like going back to really these dark periods when I received the message that I cannot come. I caught an infection, but luckily he will be able to present this talk through Zoom, and then seeing that everything works, I'm happy to give the floor to you. Thank you.
Okay, thank you very much for the very nice introduction. And my apologies that my voice is bad, and my apologies that I cannot come in person. But please, can you confirm that my slides are visible and I can be heard more or less well?
Yes, we can confirm. We hear you well. The slides are on the screen. Everything is working.
Okay, okay. They are full screen, right? And you can see my mouse also.
Yes, we can also see you.
Okay, perfect. All right. So I want to give you basically a brief discussion of two issues which I find interesting in the broad context of string landscape and swampland. This is, on the one hand, the landscape itself and the question about the sitter vacua, and then cobordism and wormholes. So let me start with the outline. I don't want to assume that everybody knows a string theory landscape. So I will give you a brief reminder of the basics. And then I will come to the recent swampland debate and the subsequent scrutiny of accepted constructions of de Sitter models like KKLT and LVS. And finally, I will come to a few other swampland-related issues, namely wormholes and cobordism conjecture, which are quite speculative, but I think are nevertheless very interesting. All right, so let's start. So there's an almost unique starting point, which is, of course, the hallmark of string theory, namely the worldsheet theory with two-dimensional supergravity embedded in d dimensions. I have drawn here the famous picture where a string propagates and, for example, splits into two further strings, and a particle splits into two particles. On the string worldsheet, you have the fields which describe its embedding in spacetime and also fermionic partners. So this theory is very easily defined and then has an enormous richness of solutions. Crucially, the theory works only in 10 dimensions, a number which is then uniquely fixed. And there it produces an almost unique 10-dimensional effective theory. So now I basically go in 10 dimensions still to the low energy effective theory. And it turns out that there are several of them which are related by dualities, which I will not describe, but there's a more or less unique 10-dimensional field theory Lagrangian, which I will call type 2b supergravity. I will focus on that branch. And I want to be technical in describing the landscape, so I want to give you the 10-dimensional Lagrangian, or the action. It is written here. There's a prefactor, which is basically 1 over the string coupling squared, the Einstein-Hilbert term, then various kinetic terms for the dilaton, which governs the string coupling, and for various form fields, here from H3 to F135. These are just higher form gauge fields, basically. And then crucially, and we'll come back to that, there's a so-called Chern-Simons term. There you have a wedge product between some of these forms. So now let's go on towards the string theory landscape. And I will first start, as I promised, to review what is maybe well known to most string theorists, but as I said, I will not necessarily assume that everybody here knows that. So the first step is, of course, one wants to go from 10 dimensions to 4 dimensions. I mean, on the one hand, one should emphasize this is a beautiful theory of quantum gravity in 10 dimensions, but it's far from trivial whether this is something to do with the real world, which is a 4-dimensional quantum gravity. So the first step is to solve the vacuum equations of motion, compactifying from 4 dimensions, from 10 dimensions to 4 dimensions on Calabi-Yau's. So the reason to choose Calabi-Yau's is this solution of equation of motion, because they are Ricci flat, so the Einstein equations is automatically solved without adding any further ingredients. More precisely, we consider geometries which are R1, 3 for our 4D spacetime times x, and x will be, that's why I said more precisely, Calabi-Yau divided by some discrete group k. It is called, this quotient is called Calabi-Yau orientifold. In this quotienting, there's also an orientation change of the string world sheet, so that's why orientifold, but that's not crucial for us. What's crucial is that the geometry on which you compactify the compact space now ceases to be smooth. I give you a simple example of this, a simple visualization. Let's take a torus T2 and divide it by Z2. It's easy to convince yourself that what comes out is this kind of geometry, which now does not have any more the topology of a torus, but of a sphere, but it has in particular 4 conical singularities, which are in the context of string theory would be called orientifold planes. And the dimension of the orientifold planes may vary. From 03 to 07, this will be the most important ones for us. So 3 and 7 here stand for the spatial dimension. This is a 4 or 8 dimensional defect. And right, so it's important to keep in mind that we have Calabi-Yaus with such defects introduced by orientifolding, which will play an important role in the following. So I continue still with the discussion of the basics of string landscape. So now we obtain a 4D effective field theory. And in particular, this 4D effective field theory will include the so-called moduli, the moduli of the Calabi-Yau orientifold X. The moduli, I mean massless, exactly massless fields, flat directions, which describe the geometry, the change of the geometry of that manifold. Here there are 2 different types, which is again a key standard part of the string landscape, namely by Z, I denote the complex structure moduli. They basically describe the size of the relative size of 3 cycles. And T are the Kähler moduli. They describe the relative size of 2 and 4 cycle volumes and the total volume. There's a label of them. For them, there can be several, or there usually are several, in fact, very many for typical Calabi-Yau. The next key step is to introduce quantized fluxes. In other words, field strengths of the 3-form fields F3 and H3. These field strengths are quantized in the very same way as a standard electrodynamic field strength, a 2-form F2 would be quantized if you consider it on a 2-cycle, just by the standard charge quantization or precisely flux quantization condition. So these are switching on or turning on these field strengths correspond to a choice of discrete numbers, which you may consider to be part of the choice of geometry. And so basically we encode this into a set of vectors, Fi and Hi. And they induce a superpotential, which I will call W of Z, and which here is the product of these vectors F and H. There are some prefactors involving the fields C0 and the dilaton, and crucially multiplied by a further vector, the so-called period vector, pi of Z, which encodes the features of the Calabi-Yau. These are complicated special functions describing the particular Calabi-Yau under consideration. So from the superpotential, you then can derive a scalar potential, as the formula is given here. It's maybe not so crucial for those who know supergravity. It's very familiar. For the others, it's not so essential. There's a well-defined prescription how to get the scalar potential. And the scalar potential is such that it generically stabilize all the complex structure moduli Z in terms of the chosen fluxes, Fi, Hi. So now comes a key point to do with the Chern-Simons term I mentioned before. This Chern-Simons term results in the following fact. The flux F3 which H3 plays the role of a source for the field strength F5. And so do the orientifold planes. They also source this F5. This is a non-trivial result of the 10-dimensional theory, the study of which I will not describe, but it is a very straightforward prediction. So basically, one then has something like a Gauss law constraint. I mean, there's a zero result from the integral of d star f5 just by the Stokes theorem. And this d star f5 is the sum of the sources, and the sources are these fluxes, more precisely the wedge product of F3 and H3, and the localized sources, which are precisely those identifold planes. Let me call the two contributions N and Q, and these two contributions, N plus Q, have to give 0. This is just an absolutely hard constraint on the consistency of the theory, or of the compactification. So in other words, the flux that I can turn on is limited by the Tedpool contribution J local of the O planes. One can write this N in terms of these previous flux vectors like F times H, and the contribution of the O planes is given here. It is the sum of 1/4 times the number of O3 planes. Those are just points in the compact space, and so there's no geometry of them. And 1/2 times the Euler number of the O7 planes. These O7 planes are 8-dimensional, so they span 4-dimensional surfaces in the Calabi-Yau, and so their Euler number is what enters here. And the result of this, this possibility of switching on fluxes, but also the constraint of how much flux you can switch on, leads to the crucial fact that the landscape is huge, enormous. You know these numbers, a to the 500 or even more, that people discuss in various contexts, but it is finite. Nevertheless, crucially, it is finite. So then, at this point, Kähler moduli are still flat directions. And in the simplest case, there's just one Kähler modulus, which is the volume. And so to discover the potential of the Kähler moduli, one needs to study the model with more precision. One needs to consider so-called Euclidean D3 branes wrapped on 4 cycles instanton corrections. These are not really branes present in the compactifications, but quantum fluctuations of such branes out of nothing. These instanton corrections change the superpotential I previously described by an E exponential correction factor, which is small but nevertheless crucial. Moreover, one needs to introduce, to go to a regime where the W0, this flux-induced potential, is small, and in this case, one can see that the scalar potential now changes in such a way that it is dependent on the Kähler moduli, and there's an ADS minimum. This construction of a fully stabilized ADS minimum is known as step 1 of the so-called KKLT construction. Step 2 involves the so-called uplifting to de Sitter, which is of course crucial to describe our real world, or even to describe Minkowski, because this ADS is much too deep to be anything similar to our real world. This is done by adding anti-D3 branes, but it also requires a strongly warped region, or so-called Klebanov-Schwarzschild throat, to avoid destabilization. So this is now quite non-trivial. I mean, it's not too non-trivial, but for the talk, there's very little time to really explain that. So one has to do the following. One has to introduce a large amount of flux in an appropriate conifold region of the Calabi-Yau. As a result of this metric, which is dx squared for the 4 dimensions plus dy Calabi-Yau squared, the Calabi-Yau metric, is changed by a so-called warping factor. So there is now a prefactor here and here, which depends on the Calabi-Yau internal dimensions and the position in the Calabi-Yau. And the geometry is not anymore a direct product of external space and Calabi-Yau. And here in the picture, it is symbolized as this kind of extended region throat, where the Calabi-Yau is kind of blown to a large, this region of the Calabi-Yau is kind of blown up to larger size. There's a redshift introduced to the anti-D3 brane, which breaks supersymmetry and gives you a positive energy density. Has a small effect, and this allows control and allows to avoid destabilization of the whole space, nevertheless uplifting you to de Sitter. So if everything works, the picture is such that one first has this ADS minimum, then adds a positive contribution and gets a metastable de Sitter minimum, a very fine-tuned and delicate construction. One has to admit that full explicitness has remained elusive since finding fluxes which lead to W0 much smaller than 1 is extremely hard. We are searching here an exponentially large landscape. And also this actual anti-D3 brane in the strongly warped region is controlled only in 10 supergravity. It is not really controlled using supersymmetry or full string theory. So it's a difficult calculation which has not become fully explicit maybe. So now, based on this, these difficulties, the following situation has emerged. So this and some more important variants like LVS, which I will mention later, have remained the main evidence for stringy de Sitter. So these constructions are complicated and hard to get in an explicit fashion. And it has been proposed that maybe stringy de Sitter is simply impossible as a matter of principle. This is part of the swampland discussion. And also many people have raised the concern that maybe de Sitter as such is a sick situation from the perspective of quantum gravity, and it should not be possible to get de Sitter space in a consistent quantum gravity theory. So subsequently, due to these conjectures, it has come to a new or very careful scrutiny of this KKLT and LVS constructions. And people have tried to question these constructions and with varying success. And I will discuss now some of these points, which are focusing on what I think is most critical. So one issue that has, oh, sorry, I apologize, I have gone too far. So, one issue is the so-called singular bulk problem. So I remind you, the situation is we have this Calabi-Yau with a throat with an anti-3 brane glued in, which allows for the uplift. And this is a picture for how the potential is modified. So now it turns out that one has here the interplay of two small effects. On the one hand side, this exponentially small depth of the ADS minimum. On the other side, this uplift, which is exponentially small due to a large throat flux in the exponent, which governs the strength of this uplift effect. So it turns out that the matching between these two contributions implies that the throat, this strongly warped region, can actually not be parametrically smaller than the bulk. So one actually comes to a slightly bizarre situation when here there is the Calabi-Yau, here is the throat, but the situation must be even worse than that. The throat has to be larger than the Calabi-Yau. Now this leads to the result that this warp factor H, which I give you here again, which I introduced before, has to vary significantly, even in the so-called bulk or Calabi-Yau region. And it turns out that this unavoidably leads to the fact that this warp factor, in fact, goes negative in part of the bulk. So there is a situation when basically, since there's a square root here, the metric simply breaks down in a significant part of the Calabi-Yau, and one loses calculational control. That does not mean that the scenario KKLT is dead, but it's just not possible to generically claim that one has control of this analysis. So now there's a further version of this, LVS large volume scenario, which is a closed cousin of KKLT, with a crucial twist that the volume there is exponentially large. I will not explain how this largeness arises from the stabilization procedure. I can mention that Ignatius, who gave the previous talk, has an interesting alternative proposal. There's interesting work going on in this direction. I will focus on the classical LVS. And it turns out that this exponentially large volume, however, is not sufficient to save us from these previously discussed problems. In fact, as pointed out by Junghan some time ago, higher order curvature corrections in this 10-dimensional action, like R squared, R cubed, and so on. In fact, I'm simplifying here for the sake of this talk. The key terms are on the branes, and there's an R to the 4 term at the bulk. Let me not go into too much detail. These higher curvature terms nevertheless lead to potential loss of control. And as it turns out, control can be maintained if a sufficiently large D3 tadpole is available. the D3 tadpole is precisely this contribution from the O-planes, which I had before. So this is an equality which we already know. You remember that there's this N from the flux, which is separated into the bulk flux and the throat flux, and has to be smaller than the maximal available Q. This is the geometric contribution from the O-planes, which is basically a feature of the geometry, which you can't play around with. It's given to you in terms of the Calabi-Yaus that you are using, of which there are finitely many as far as we know. So basically, one would want the contribution and bulk from the fluxes in the bulk to be small, because one already needs a lot of flux here in the throat to make the throat deep enough. And so together, it turns out that this situation becomes worse in view of higher curvature corrections in the throat, since controlling those enforces very large and throat, as I described before. So as a result, given that the known geometries have limited Qmax, one wants to stabilize all complex structure moduli with as small a bulk tadpole and bulk as possible. However, there has recently been raised the possibility, or has been suggested, that a so-called tadpole conjecture holds, which claims exactly this to be impossible. It claims that if some flux vector stabilizes a large number n of complex structure moduli, then n flux has to be bigger than alpha times n, with alpha being an order 1 number. So if you have many complex structure moduli, which generically you want to have for the sake of having a large landscape, then you need a lot of flux. This conjecture has several strong and weaker forms. I will not discuss them in detail. There's also been the discussion of certain counterexamples, in particular to the stronger forms. And there's an ongoing debate about this conjecture, the quality of control issues for KKLT and LVS, as well as efforts to find geometries with a large Qmax, this O-plane contribution to the tadpole. So this is the very interesting and controversial situation about the sitter in the string theory landscape. So now, for the last bit of the talk, I will turn to something completely different, namely, also in the context of landscape, cobordism. So just forget what I said before, focus on a new topic. Very simple topic. Two manifolds of dimension d are cobordant if they form the boundary of a manifold of dimension d+1. So, for example, obviously by this picture, an S1 is cobordant to two S1s, and S1 is also cobordant to nothing. In this case, two-dimensional gravity, but this obviously extends to other dimensions. Now comes the so-called recently raised cobordism conjecture. It says that in quantum gravity, all cobordism groups are trivial. In other words, everything is cobordant to everything. One of the key arguments for this very strong conjecture is based on the no global symmetries conjecture, which is one of the most sacred swampland conjectures. I will not discuss in detail the derivation and the arguments. Well, it's not really a derivation, it still remains a conjecture, but there's good supporting evidence. And there's a general underlying feeling that quantum gravity should allow any geometry to change into any geometry. So let's accept the cobordism conjecture. The implications of this are very strong and very non-trivial. For example, it predicts new defects or new branes. So think of this picture here. If the spin bundle of this over this S1 here is trivial, then of course, naively, there's no such cobordism, right? Because if you have here the boundary of a disk topologically, then the spin bundle on this S1 would not be trivial. There would be a 360-degree turn. So if you want an S1 with a trivial spin bundle to be cobordant to nothing, which according to the conjecture should be the case, then you need a new type of brane, which somehow gets rid of this spin twist. So it actually, this conjecture actually predicts new objects. Moreover, and this is another obvious implication, you cannot avoid the creation of baby universes. So basically, a spacetime can emit a sphere. I draw here 2 dimensions, but you should think, of course, of our real world. I mean, a 4-dimensional spacetime can emit a 3-sphere as an extra baby universe, or 2 of them, and so on. Now, this baby universe story is, of course, a very old story. It goes back to getting Strominger, Coleman, Preskill. Coleman's original analysis allowed us to save us in this context from the apparently horrible non-locality that is introduced, namely by rewriting this whole baby universe summation or wormhole summation in terms of alpha parameters. So a baby universe being emitted and absorbed corresponds to such a wormhole geometry, and summing over all this wormhole geometry gives you this exponentiation, but then you can rewrite it like this using an alpha parameter, and the integral over alpha will reintroduce this non-local expression, but in this form here, it's a perfectly local theory, but there is a new parameter somehow introduced which describes the, roughly speaking, baby universe state, which is adjacent to our spacetime, which exists in addition to our spacetime. Now, recently, there has been some interesting new discussion and progress here. There has been a celebrated toy model by Marlow and Maxfield, who were able to explicitly solve by introducing also connections of 3 or more such wormholes, explicitly solve in 2 dimensions this summation. And this Marlow-Maxfield toy model turns out to have an unexpected reduction of the Hilbert space. Namely, it turns out that there's a gauge invariance which has to be modeled out, and the Hilbert space of this baby universe, this extra freedom in addition to our spacetime, is much smaller than expected. Now, on this basis, it has been conjectured that in d equals 4, this reduction is so strong that the Hilbert space of baby universes or alpha parameters becomes even one-dimensional, such that there's basically no such unwanted extra freedom in addition to our spacetime. Which, by the way, this freedom, as you maybe can see from this picture here, from this formula here, this freedom corresponds to coefficients of operators, which then become dependent on the baby universe state. So this is a very controversial story. It has remained, so many others have struggled with the question whether string theory really possesses these underlying wormhole solutions. I listed a few of the authors who worked on this over the recent years, and in particular also very recently. And let me emphasize why it is for some people so important to get rid of these baby universes. A key problem is that even after Coleman's resummation, which apparently turns things local, this fundamental underlying non-locality still clashes with the locality of ADS-CFT, which, as you know, for string theorists thinking about quantum gravity is kind of a sacred assumption. So here is a picture, a sketch of what I want to tell you. This is the ADS space, this is the CFT living on the boundary. The fact that you have wormholes here clashes with the locality of the CFT on the boundary. So on the other hand, there's the recent success of wormholes in the black hole entropy context. For example, for the derivation of the island formula suggests that wormholes are really relevant. So this whole wormhole baby universe theory remains mysterious because there are strong arguments both in favor and against the physicality of these baby universes and the baby universe state. So you can find the recent literature by following these relatively recent papers by Marov, Maxfield, and McNamara Wafa. That brings me to the end. I hope I have not been too much over time. So string theory remains a leading candidate for a fundamental theory of quantum gravity. The realistic landscape of flux vacuum, the SUSY breaking, and positive cosmological constant has come under pressure due to doubts raised in the swampland debate. On the positive side, this has led to a new precision era in the construction of explicit string quantifications. The old story of Euclidean wormholes and baby universes has seen a revival due to the prominent role of wormholes in the black hole entropy context. And explicit toy models and new ideas for avoiding the problematic implications of the baby universe state are being discussed at this very moment. Thank you very much.
So thank you for delivering this great talk. It was a pleasure to listen to here from the audience. Are there questions? Daniele.
Yeah, thanks for the talk. Can you say something more about the clash between the wormhole story and the locality in ADS?
Yes. So if you introduce the alpha parameters to describe, to resum these, so basically you have to have your ADS bulk and you have to add in all these wormholes. And then you write the story in terms of the sum over the alpha parameters, as I gave you before. Look at this here, right? Then it turns out that you basically are arriving at a situation when it looks as if you have an integral over alphas, and for each value of the alpha, you have separate CFT. But you want the quantum gravity, or maybe you want the quantum gravity, it has also been the opposite conjecture, by the way, maybe you want the quantum gravity to be dual to one CFT. At least that is what one naively expects in the ADS CFT context. And so basically, having the alpha parameter somehow corresponds to what people have also called an ensemble average ADS CFT, which maybe is really the case in 2 dimensions in the context of SYK, but this is a special case which one does not really want to hold in 4 dimensions. I mean, it's simply open whether one should somehow get rid of the wormholes or reinterpret how they are included in quantum gravity, or whether one maybe very, courageously should claim that ADS CFT is only an ensemble average statement, so that the dual is not one CFT, but a sum of many CFTs weighted in a certain way by the alpha parameters. Does that answer the question?
Yes, there are more questions, and probably much more questions that we can take at the moment. So Sumati, and then we take 2 here.
Just a quick question, which is with these cobordisms, when this conjecture says that in quantum gravity that the cobordism is the group is trivial. We know that in the Lorentzian case, there are restrictions because not every 4-manifold or n-manifold admits a Lorentzian metric. So are these statements within the Lorentzian context or for Riemannian signature spaces?
Well, one has to honestly admit that these are statements, this is a physics conjecture. This is, of course, not a mathematics conjecture. I mean, it's clear that this, for example, let's go back to the simplest picture. It's clear that on this geometry here, one does not really have a smooth Lorentzian metric. So in string theory, where this diagram is typical, this is not a problem because one usually does these calculations in a Euclidean setting. But the cobordism conjecture states that there must be really a physical process. I mean, the statement is, by saying the cobordism groups are trivial, is that there's really a physical transition between this situation and this situation. So I mean, we all know that this is a famous problem, this absence of a Lorentzian metric, but the claim is that due to quantum gravity, it should be possible to transit from one geometry to another. I mean, if I had time, which I think I don't have, I could explain why, if I don't have such transitions, then it's easy to construct a situation where you basically have something akin to a non-decaying particle or non-decaying defect, which is not protected by gauge symmetry. So that should not be the case. And therefore, one simply proposes that this process is possible. What calculation then, of course, goes as one usually does by transition to Euclidean and then some form as analytic continuation. But I totally admit that this is a quite open question, and it's of course possible that this is wrong and topology change is strictly forbidden, at least in such cases. I am not going to make a very strong statement. I'm just saying this is something which is very hotly debated at present.
Then the last question for the session. You can just pass it through.
Yeah, so are these wormholes supported by any topological charge? I guess axion charge, right? Is it necessarily only the axion charge?
Very good point. Yeah. So I, for time reasons, I skipped the fact that for these wormholes, for example, this one, there's explicit solutions. Gidding Strominger calculated this solution for the case that there is basically an axionic charge flowing through this wormhole. So roughly speaking, if you cut it transversely, there's a three-sphere, and you have the dual field strength F3 quantized on this transverse cut, which is a three-sphere. That supports the wormhole and makes it a solution. But of course, for the broader context of having these wormholes in the localities, it may not be necessary to have a solution. It may just be sufficient to have the topology. So I have no strong opinion whether one should base these wormholes exclusively on those which are which possess explicit solutions due to Giddings and Strominger and related to axions, or one should extend it to all such geometries where two distant points are connected by a wormhole, which maybe in principle would collapse because there's no solution, but nevertheless, as a quantum fluctuations, it could contribute to the total partition function. So,
yeah. But if we think of a quantum gravity theory which doesn't arise in this way, through extra-dimensional, I mean, where you have such extra-dimensional fields, then we don't see these effects, right? Because you don't have any axion fields or other fields which can give you the charge.
Right. If you, for example, assume that only such wormholes are relevant which correspond to solutions, I mean, really solutions rather than just quantum fluctuations. And you, in addition, assume that you have no axions, which is possible, but I mean, unlikely because axions are a very simple ingredient in many situations. Then you would indeed not have such baby universes. I mean, that would certainly be one way out of the story. But I think that once you allow, in principle, topology change, then you should include such wormholes even then when they do not correspond to a solution. But that's an opinion, and it is unclear. I admit to you that there are various ways to get rid of them.
Okay, thank you.
Okay, so thank you very much for this nice talk. And before leaving, let me make two short announcements. So lunch is in a different building. In your registration package, you should have a lunch voucher. So these are necessary there. And then the poster session will be in the same building as the lunch, just going down one stair. And then we reconvene for the parallel sessions in this building. The parallel sessions start.
Thank you. Bye.